Okay, good afternoon, everyone. Let's start the afternoon session. The first speaker is Adrian Fenguin, probably the happiest man in the room for Argentina, but he's based now in Northeastern University. Adrian, please.
Thank you, Jose. First of all, of course, I want to thank Jose for organizing such a wonderful school and conference, and taking care of all the logistics and doing such a great job, taking care of us during this week. And of course, I want to, I'm honored to be here to celebrate Chico's birthday. Congratulations, happy birthday, Chico. I know it's on Saturday, but I'll tell you in advance. And it's a pleasure to be able to visit Sao Carlos and tell you about my research. For those students that were expecting me to say something about machine learning, I apologize in advance. I changed my mind. But I gave Jose all the missing slides from yesterday's lecture, so you can see the rest of the material there. So today I want to tell you about something else, some projects, some ideas we've been working on for the past 2-3 years in my group. It's about calculating time and momentum resolved spectroscopies in strongly correlated materials using a quite new approach. So most of the work I'm going to present today was done in collaboration with my former postdoc, Crisia, who actually was a student here in Sao Carlos with Luis. And now she's in Dublin. Actually, she moved from Royal Holloway to Dublin. I should update that. Alberto is my former postdoc. He's now in UBC in British Columbia in Canada. And Luhan Yang is my former student. She's now a postdoc in SLAC in Stanford. And Philip Weinberg, my former postdoc, is now, he betrayed me. He's studying in the back. He moved to the private sector. He's working in a quantum computing company, QERA. It's a Rydberg atom company. All right. If Philip is watching this or watches it, it's a joke. So what is this talk about? So in the past, as I mentioned, in the past couple of years, we've been developing new computational technology to calculate these time-resolved and non-equilibrium spectroscopies. And today I want to walk you through many of these ideas. And I want to explain why this is such a challenging and pressing problem now in our field. Well, the main motivation, of course, is the huge interest in the community in non-equilibrium physics and probing non-equilibrium excitations of systems away from equilibrium. And for this, there have been huge investments in the US and elsewhere on new photon sources to probe materials with X-rays. And so the agency that built these labs or sponsors these labs is the agency that pays me to do this. So I can't disappoint them, right? So that's the Department of Energy. So well, I'm going to walk you through several different kinds of spectroscopies. So the plan is to come up with numerical ways to help experimentalists to interpret their spectra when they do non-equilibrium photoemission, non-equilibrium neutron scattering eventually, and other kinds of spectroscopies such as Corehole Spectroscopies, X-ray spectroscopies. So I'm going to start with maybe the simplest one, the one we are more familiar with, which is time-resolved photoemission. Time-resolved photoemission is nothing else but an application of the photoelectric effect. You shine a laser on your sample, the photons kick out electrons, and you measure the energy and momentum of the outgoing electrons, and you can tell what the dispersion or the spectrum of these electrons is in the bulk of the solid. And if you go to a condensed matter book or a quantum many-body book, they will tell you the photoemission spectrum is just the imaginary time of the Green's function. And that's it. Live with it. They don't tell you why. They don't tell you where it comes from. So today I'm going to try to give you some motivation where it comes from, because this is basically key to understanding what we are trying to do. But before we go to equilibrium, I want to show you here what happens out of equilibrium. Out of equilibrium, it's no longer just the Green's function. This becomes a complicated object. You have to do time-dependent perturbation theory, and you have to do it in the Keldysh contour. And now you have I think the order of the slides is incorrect. Yep. All right. All right, so you have to do it in the Keldysh contour, and you get this nasty, complicated expression there that, if you look at it, it doesn't look like a Fermi golden rule. It doesn't look like, Green's function. It's something that contains matrix elements between all excited states, N and M, and a delta function that also contains the energy difference between excited states, N and M, and everything is inside a square. So this is a very complicated quantity to calculate. If you want to do it analytically, forget about it. I mean, you can try numerically, but then since you have the entire spectrum, you need the entire spectrum and you need all the eigenstates, you need to do exact analyzation in small systems. So that's all you can do. But we know, and if you want to evaluate this integral, people have tried to do it explicitly by doing the time evolution and calculating this sum, which is in the time domain instead of the frequency domain. But then they don't know how to do this two-time integration. It's very difficult numerically. And there are different approaches in the literature that you may encounter, but sometimes they introduce artifacts such as negative spectral weights and crazy things like that. So still, these approaches give you quite good intuition about what to expect, but rigorously speaking, they don't describe the spectrum observed in the experiments. So what do the experiments, well, in equilibrium, as I mentioned earlier, you get the Fermi's golden rule. So how do you derive Fermi's golden rule? So let's start from the basics. So you have a Hamiltonian. I hope you can all read the font size of there. That has the Hamiltonian of the system you are interested in, H0. There could be any many-body model you are studying. And then has a piece which is the photon bath. And photons are bosons, so we know that numerically they are very difficult to treat, but there is a nice assumption that's going to come in our help. So then we introduce a perturbation, which is the light-matter interaction. Light-matter interaction enters as a term that destroys a photon, destroys an electron in the material, and creates an electron in the scattering continuum outside of the material. Right? That's the C tilde dagger. And of course, the Hermitian conjugate as well. And then you do perturbation theory, starting from the ground state, and a state with no photons in the, so you put a source and you put a detector, say at momentum k, and then you mention you measure the occupation of this mode k as a function of time. That's what the detector is doing. So you just measure, you shine the photon and you measure as a function of time the occupation, with the detector, how many electrons you capture with momentum k and certain energy omega. And that's what is described there. And you end up with, after you do a simple calculation in a couple of lines, you end up with the Fermi's golden rule. And so far, so good. This is an expression that can be efficiently calculated using Green's function formalism, can be efficiently calculated using numerical normalization group, density matrix normalization group, quantum Monte Carlo, using max entropy and other analytic continuation techniques, dynamical mean field theory, and so on and so forth. All these methods calculate basically this quantity. But now when you're out of equilibrium, again, you end up with this nasty expression. And we started scratching our heads trying to figure out how we can calculate this expression with DMRG. And it actually, in the beginning we were looking at this two-time integral. Maybe we should calculate this two-time integral. How do we do it? And then we realized maybe we don't need to do that. Maybe we should look at how the experiment is carried out and what we are measuring. And how about we put the photons, we put the detector, we put the scattering term, we put everything in our calculation, and we let it evolve. So we're evolving the system in real time, but we're evolving the scattering process, right? We're simulating the scattering process. We're simulating how a photon comes, kicks the electron, and we measure the electron, without thinking in terms of Green's functions, in terms of scattering cross-sections, in terms of frequency. Instead of working in the frequency domain, we are working in real time. And well, after some trying different ways to do this, we came up with one approach. I'm showing you first this one, which is, I call it the tunneling approach. It doesn't have the photons, because the incoming photon can be replaced by a classical field, like a chemical potential. And then what we do is the following. I'm showing everything in one dimension because it's easier to visualize. We put a sample that we want to probe. That's our chain, the sample chain. And then we put, attached to every site of the chain, a probe. It's like an empty orbital. It's going to be empty. It's like an STM probe on it's on every site, every atom of your sample. So you know that STM makes a local measurement. You know, you move your tip, you put it on top of an atom. Here we put many STM probes, one on top of each atom, right? And then we turn on a hopping between the sample and the probe, and we let it evolve. And as the system evolves, we measure the occupation of the mode n of k. So what we have to do is measure here. Let me see if, no arrow, oh there, whoop. So we measure this quantity here, which is nothing else but the momentum distribution function of the electrons on the probe chain as a function of time. I hope this is more or less clear. So the idea is that, you know, you have, suppose that this is a Hubbard model. This is your density of states. This is the lower Hubbard band. This is the upper Hubbard band. And then you put your probe chain. It has no dispersion, right? Because you know, all these sites are disconnected. There's no hopping between the orbitals in the probe, only between the orbitals in the probe and the orbitals in the chain. And you move them up and down using a gate voltage. And depending on the gate voltage, if there is an electron at that energy, it's going to tunnel. If there are no electrons at that energy, they're not going to tunnel. So you have energy conservation, and you have momentum conservation. So this is basically a faithful description of what the photoemission experiment is doing. And to illustrate how it works, it's probably easy to see a non-interacting case, just a tie-binding chain, one-dimensional non-interacting chain. And this is just a hopping Hamiltonian that we can transform to momentum as this. You know, it's already diagonal. Then we have a probe. Since the probe is also translational invariant, we can write it in momentum. And we have a tunneling Hamiltonian, which is also translational invariant, and we can write it in momentum. So we write everything in momentum, and it becomes a 2x2 matrix, connecting a mode k on the chain and a mode k on the probe. And we let it evolve. We start from the ground state with, say, mode k filled or mode k empty, depending on how many electrons you have. And then you look at the occupation of the probe orbital as a function of time. Right? This is a simple quantum mechanics problem that you can, I mean, any student in Quantum 1 can do in like 2 lines. And you see that as a function of time, you see this is done at momentum 0, so the energy is 2. And you see that you have like a little blip. And as you evolve in time, this blip evolves into a sharper and sharper peak. And this is, in the infinite time limit, it becomes a delta, right? And it becomes Fermi's golden rule. You recover Fermi's golden rule. And the catch is that you have this ringing. You see these little blips, the satellite peaks. And these satellite peaks are because this is not, you know, for finite time, you don't get a delta. You get something that's a sinc function. A sinc function actually, if you do an ultra-fast experiment, you actually see this ring in experiments as well, right? It's not an artifact, it's physics. This is basically the energy, time, uncertainty principle. The longer you measure, the more precision you get in the energy. The shorter the time, the less resolution you get in the energy. So here I'm showing you an example of a calculation in which on the right you're going to see how the spectrum evolves in time for an interacting system. This is an extended Hubbard chain with after quench. So we start from a value of the parameters that is very in the most insulating phase, and we quench to a value of parameters that is very close but not quite into a charge density wave phase. And now the system is going to be very far from equilibrium after the quench, and after we do the quench, we connect our system to the probe and we start measuring. And this is what we get as time evolves. So on the left, you see the top panel shows the evolution of the spectrum as a function of the probing time, and below as a function of how much time you wait before you start measuring. And you see that the spectrum, in this case, doesn't change much, because the energy scales for these processes is very, very short compared to the measuring time. So to just give you a little bit of physics intuition of what's happening, on the left you see the density of states of this model after the quench in equilibrium. The lower Hubbard band is occupied, the upper Hubbard band is empty states. Right? At finite temperature, so if you crank up the temperature, you'll see something like this on the right, which is quite counterintuitive, but this here, this kind of spectrum is something called spin incoherent Latinger liquid. I don't want to spend time on the spin incoherent Latinger liquid, but the physics is well understood, has to do with spin charge separation. But then you start seeing that there is some weight, there's some spectral weight in the gap, and some spectral weight up here in the upper Hubbard band. Right? You have to have a little bit of imagination, but you see a little bit of purple up here, a little bit of purple here. Now, this is on the right what we find, which is completely different. Right? So it's a spectrum out of equilibrium, and it's clearly non-thermal. So you cannot associate the spectrum after the quench to any spectrum at any temperature. And the reason is that this is not an integrable system, but has spin charge separation, and is relatively close to integrability. So the relaxation is very, very slow, and in some cases, some processes are completely forbidden. So it can never really thermalize. An interesting thing is that you see here this sharp feature in the gap. These are excitons, and so these are bound states of doublons in the upper Hubbard band and holons in the lower Hubbard band. Then you see anti-bound states at the very bottom, high energy. And these states here, where my cursor is, are in the gap, below the upper Hubbard band. And this is because these are states that, because the excitation spectrum out of equilibrium measures transitions between excited states, not between excited state and the ground state. Right? So you don't expect to have the same gap in equilibrium and away from equilibrium. In other words, this is something called photodoping. It's like you're creating particle Hall excitations. There are transitions into the upper Hubbard band. When you populate the upper Hubbard band, you start seeing these transitions that appear there. So now this is the latest thing we've been working on, and but not the last I want to show you. But it sort of comes right. I mean, conceptually, it's a continuation of the previous idea, and it's motivated by recent efforts in several experimental groups to actually measure this 2 electron tunneling spectroscopy. And this is something that people in Canada is trying to do. We have a collaboration with Andreas Damascelli, and hopefully we'll be able to compare experiment and theory soon. The idea here is that when you shine a laser beam on your material, you're not having one photon hitting at a time. You have many, many photons hitting at a time. And you may hit more than one electron out of your sample. You can hit, at the same time. And you can, if you have two detectors now, you can probably measure simultaneous collisions and correlations between electrons in the bulk. So the way it works is as follows. We have now well, the same as before. We have a bias, and then the tunneling. Now I replace the chain. So before I was measuring n of k, right? But I can measure n of k with a single orbital in a momentum k, right? Instead of putting a parallel chain, I can Fourier transform my probe and write it in momentum, and then I will get one of these stars. Then the Hamiltonian becomes non-local because I'm mixing real space for the physical system and momentum space for the probe, right? So the probe now is in momentum space, the physical system is in real space, so I'm missing representation in k space and representation in real space. And then the Hamiltonian becomes non-local. I have that the hopping now is between the orbital k and all the orbitals in the chain. And if I have a second detector at momentum k2, I put it the same way there. And now I can measure, as a function of time, correlations between the two detectors. If you want to do the perturbation theory for this problem, you end up with a very complicated expression. It's much more complicated than the one before. And the reason is that the Hamiltonian contains only single photon, single electron terms, right? You destroy a photon, you create an electron, you kick out an electron. You don't kick out two electrons. To kick out two electrons, you need to come with the photon first, kick out one electron, with the photon after, you kick out the second electron, right? So you have to do higher order perturbation theory in order to get two electrons out. And that's a very complicated expression to evaluate, but we can do it with our time-dependent approach. So we evolve it in time, and this is the spectrum. So I'm going to explain what I'm showing you here. This is momentum K1 on the horizontal axis, momentum K2 on the vertical axis, and we measure the correlation between K1 and K2. And then what we do is we measure at different energies. So we change the energy and we measure. These are different cuts. This is what you see in an RPS spectrum typically when you see a Brillouin zone at different energies. So as you increase the energy, you start seeing this, and you see that there are two peaks that appear there along this diagonal. And these are peaks that mix momentum k and minus k. So now I'm going to plot this along the diagonal. So I'm going to make a cut along the diagonal and see what it looks like as a function of frequency or energy. And this is what it looks like. So on the left, I show you the correlation between up and down electrons and momentum k and minus k. By the way, this is a Hubbard model with negative u. So I made it attractive because I'm interested in looking at correlations between electrons in the superconducting state, right? I want to probe for pairing. And you see that it looks very peculiar. You have this feature here that looks like a band. By the way, this is a small system. This is 16 sites only. Right now I'm running larger system sizes, but these are very expensive calculations. And then you see these two blips up here. Now, if you measure the correlator up, you see basically, of course, this dark area in the middle because you cannot have, because of Pauli's exclusion principle, you cannot have two electrons up on k equals 0. But then you see the rest of the spectrum, and k and minus up and up are uncorrelated. So this should be the same as two uncorrelated electrons. And And then you can measure the n of k and n of minus k separately, and you can subtract it from the spectrum up here on the left, and you end up with the connected, if you will, correlator, right? So the actual correlations between the electrons. And that gives you basically these two blips that we had at momentum kf and minus kf. And it's nothing else but the structure, the internal, this is telling you what the internal structure of the Cooper pairs is, basically. It's basically telling you that Cooper pairs are formed by two electrons at the Fermi momenta, kf and minus kf, with opposite spin. So you're basically probing the internal structure of the order pair. All right, I have 5 minutes. I've been talking too much. So other things that you can do is studying Corehole Spectroscopies. The idea is to, this is a more complicated non-equilibrium spectroscopy in which, imagine you want to probe the excitations in your bulk, and you have a deep localized level, like could be a core, it's a core orbital typically, S or P orbital. And what you do is you shine light to promote one electron from the core orbital to the valence band or conduction band. And then you're going to leave a hole behind. And this hole acts as a scattering center. It's like an attractive potential because it has a positive charge. And it creates a lot of particle Hall excitation. So there's a transient time in which it creates a lot of particle Hall excitations. And then there's a spontaneous emission. An electron in the band recombines with the electron in the core and emits a photon. And you measure the energy lost, basically the difference between the momentum and energy of the outgoing photon and the incoming photon. You can write the problem, again, calculating the spectrum is very complicated. It involves all this mixing between different excited states. You need to calculate all the spectrum, all the eigenstates, and calculate all the sandwiches. So here what we do is we use, again, this time resolved scattering approach that we invented. So the idea is that we put all the terms in the Hamiltonian, we put the photons, we put the core orbitals, we put the light-matter interaction, we put the dipole term that creates the particle Hall excitation. You simulate it in time, and you measure. So you have to put the detector as well, and you measure. So if you do the perturbation theory, that's the expression that you get. It's called the Kramers-Heisenberg formula, and it's very difficult to evaluate. So, and this is for the Mott insulating Hubbard chain, and this is how the spectrum evolves as a function of measuring time. So above, you see the geometry that we used. And it turns out that the low energy part gives you, this gives you sort of neutral excitations because you have a photon coming in and a photon coming out. There are no electrons coming out. So you end up with excitations that have the same, pretty much the same quantum numbers in terms of particle number as the initial state. So what you measure below at low energies is the spin structure factor, basically the same as neutron scattering. And at high energies, you measure the charge structure factor. Finally, to wrap up, this is something, so the same as the two-electron photoemission. This is not published, it's work in progress. This is that I'm showing you now, it's also work in progress. We are going to post the preprint on the archive next week. So we can introduce, so the question is, in this expression up there, that's the expression for the Rix spectrum that I showed you earlier. There's an imaginary constant there, I eta, in the denominator. That's supposedly, it's a phenomenological constant that is associated to the lifetime of the core hole, right? So how long it takes for the core hole to recombine with an electron. And this is, no one knows, exactly how to calculate this. So the source of the, what determines the lifetime of the core hole is, there are a lot of variables. But the most important ingredient is Auger recombination. This is non-radiative recombination. So besides recombining and emitting a photon, you can recombine, as shown here, you can have an electron that recombines with the core level and an electron that goes at the same time into the scattering continuum at high energies. So this process conserves energy, and it changes the quantum numbers of the system. You clearly see that an electron is kicked out, like in photoemission. And this and RICS happen exactly at the same time. They're both happening simultaneously. So we can add this process to our calculation. And the way we do it is by introducing the scattering continuum. We can do it only locally. We cannot do momentum resolution, but most of the RICS measurements don't have momentum resolution anyway. And this, basically we need to put all these degrees of freedom. We put the scattering continuum, the photon source, the photon detector, the Corehole, and we have radiative emission and non-radiative recombination at this. So radiative recombination and non-radiative recombination happening at the same time, and we can study how, as a function of this Auger coupling, the spectrum evolves in time. And basically, you see that, well, there's no surprise here. We see that the main effect is to change the signal, the amplitude of the signal, because you have the lifetime of the Corehole is shorter, or basically you have less photons going out. And if you have less photons going out, your signal goes down in intensity. Okay, so I guess I have to wrap up, or I want to show you also Auger photoemission, but I guess if you're curious, you can ask me later, and conclude with this slide. And basically, we have come up with the time scattering approach that allows you to calculate time result spectroscopies and Corehole spectroscopies away and in equilibrium. That doesn't matter. So the state of the system can be, in equilibrium. It could be, as I showed you, the result of a quench or a pump. And it overcomes all the limitations of previous methods that were trying to, they were focused on doing everything in the frequency domain instead of the time domain. And we use DMRG as a solver, but the idea doesn't depend on what solver you use for the time-dependent Schrödinger equation. You can use time-dependent. Actually, Martin Eckstein and Philip Werner have done dynamical mean field theory, and you can extend it to other, many kinds of spectroscopies, as I showed here. We have ideas for other types of experiments, and it will allow us to hopefully compare to actual experimental results. And with this, I want to thank you again for your attention. I'll be happy to answer questions, and happy birthday.
Thanks a lot. So, questions? Yes.
Yes, that was some really impressive results you had there. I just had lunch, so I missed something on the earlier slides there. You had some beautiful results, and then there is a T-weight and T-probe.
Right.
What are the differences between the two?
You can play different tricks. So you can apply perturbation, wait some time before you start measuring. So that's T-weight. And once you start measuring, you measure for some probing time. So that's T-probe. So T-probe, typically we take it to be constant. We see how the spectrum evolves as a function of T-probe. And when the resolution is good enough, we are happy. But T-weight can vary depending on, if we want to study a transient regime, we can vary T-probe and see how the spectrum evolves in time.
So basically the T-probe, you take it as large as you need, but not larger.
The T-probe is not what?
You take it as large as you need, but not larger.
I can't go here. Okay. Maybe. So one comment, in this Auger spectroscopy that I didn't have time to tell you about, we have other time scales because we have the time scale for recombination, and we have the length of the pulse we send to probe the system. So we send a pulse to probe the system, and this pulse has a length. So we also have an additional variable in this problem, but I can tell you later.
Following up this question, do you have an idea of how you showed a movie with a T going 1, 2, 3 in units of what, and how
1 over the hopping.
And in milliseconds?
No, this is like femtoseconds. Yeah.
Okay, so how?
Well, actually, what I'm showing you here in reality is like picoseconds, but
very hard to probe experimentally.
It's exaggerated.
So seeing the movie experimentally is kind of hard.
Yes.
Okay.
Yeah. So we have to move to the femtosecond scale, and that's what I'm working on right now, basically.
Okay.
What we have to do is rescale the Hamiltonian and be able to measure, making time tiny, compared to the rest of the variables in the system.
Regarding the Corehole Spectroscopy, there's this very old problem of the X-ray edge singularity, which I suppose is the large time limit of your spectroscopy, but then you need the metal, and you did it for the moth insulator, right?
Yes.
But I suppose you could use this method to try to see how the X-ray edge singularity evolves with time. Do you think you can do that?
I know where you're going with that. Yeah. There have been some recent experiments in the Harvard group where they measure X-ray absorption as a function of time after a pulse, and they see that the gap changes in time. And they argue that with the pulse, they are changing the magnitude of the Hubbard U, right? And I don't believe that. But in any case, yes. So here I'm showing you X-ray scattering, resonant inelastic X-ray scattering. I'm not showing X-ray absorption, but X-ray absorption, we did X-ray absorption too. And yes, we can do that, but we haven't done. So here we did X-ray absorption in equilibrium to look for the transition edge, and we fixed the energy of the photon to that energy, and then we calculated the Rick spectrum. Yeah, but then for the non-equilibrium problem, we can do it. We haven't done it, but it's in our to-do list.
Okay, thank you.
More questions? Well, if not, let's thank Adrian again for this very detailed, scattered talk.
My pleasure. You have HDMI? Yes.
Can you hear me? Yeah. Okay.
Next speaker, Erik Sorensen from McMaster University. Erik, please.
Thanks a lot. So it's really a pleasure to be here. It's my first physics meeting in Brazil. It's been a pleasure to be here all week. So first of all, great thanks to Jose for organizing it, and secondly also happy birthday to Chico. I will miss the celebrations on the real birthday on Saturday, but I'm sure you will enjoy it. So I'm going to tell you a little bit about some recent work that we've been doing on Kitev spin chains, and I'm probably always going to run out of time. So if I do that, there's a couple of references here that you can look at a later point. So this is some work that I've been doing mainly with Hye-Young Kee from the University of Toronto, and then a motley of students both at Toronto and McMaster University. So if you were here for the summer school, you have already heard about Kitev's very famous models by now, showing exact results for models that have anionic excitations. And the one that I'll be referring to or coming back to today is the Kitev honeycomb model. So it's a deceptively simple model. It only has Ising interactions. And the new thing in this model is that the interactions are bond dependent. So you don't have the same Ising interactions in all the bonds. It depends on the bond's directions. And that's what gives rise to all the interesting physics. If you look in detail, you'll see that if I do a product of the Pauli operators around one of the hexagons here, then that actually commutes with the Hamiltonian, and that gives us a huge number of constants that we can use to exactly solve the model. I just want to bring you to the attention that, do I have a pointer? I don't have a pointer. Well, doesn't matter. The will this one show up? Oh yeah, you can. I can use this one. If you look here, then the bond directional interactions, they're arranged in this particular manner. And what I'll be focusing on today is just looking at a sort of a slice of this honeycomb lattice, and hopefully I can look at some interesting physics when I do that. So that work was from 2002 and 2005. Okay. Then that was, of course, very exciting, but the real excitement, it came a couple of years later when Diagonalizations and Llewellyn, they showed that you can actually hope to realize materials that have very interactions that are very close to these bond-dependent Ising interactions. And this happens if you look for materials that have edge-sharing tetrahedra, because the usual Heisenberg interaction that you would expect to arise, that cancels out, and you're left with Ising interactions that will depend on how the tetrahedra are arranged. So this immediately set off sort of a search for materials, and today there's a whole class of materials that are called Kitev materials that have bond-dependent interactions. That's what sort of quantifies the class of materials. But there are other interactions here that I won't really talk about today, but due to the large spin-orbit coupling and the strong correlations in these materials, then there are other interactions, and the material that I'll be referring to, I won't really discuss it today, is alpha ruthenium trichloride. It's the one here in the box. And that's one of the best realizations of this Kitev material that we have today. Is it me that's making the bumps there for the audio? But the other interactions that we're neglecting today, they actually give rise to magnetic ordering. What I want you to remember is that there's hope for having realizations of these models, but probably if I go down to very low temperatures, then the residual or vestigial interactions, they're going to come in and actually induce some ordering that we're going to somehow try to get around. So let me show you some actual results here to Well, there's one thing I should point out, that most of these material actually have ferromagnetic Kitev interactions. So the Ising terms that occur there they should induce ferromagnetic ordering. So let me show you some results. These are fairly recent. There's a huge activity, and there are many results I could show. I just want you to focus on these results here, and what they indicate is, remember that I mentioned that there should probably be ordering at low temperature. You can see here in alpha ruthenium trichloride, it appears that the ordering, it's around 7 to 8 kelvins, but I can try to kill off that ordering by putting the system in a magnetic field. Or I could also studying it right above the ordering transition. And in this case, they put in a field in the A direction. And what is there are now a number of experiments that indicate that there's a very interesting phase sitting above this ordered phase in a magnetic field. The precise nature of this phase is hotly debated. And hopefully what I'll show you today will shed a little bit of light on it. If you believe in the Kitev honeycomb model that I showed you, then you can also try to work with that, and there's a lot of numerical results for it. So if you just do 24-site exact diagonalizations, you have to satisfy all the symmetries, so it's fairly limited, the cluster sizes that you can really look at. Then the integrability of the model, it's destroyed by the presence of a magnetic field. So you have to do numerics. And then over here, you can see, indeed, it looks like there's a phase that's sitting here that could be potentially a spin liquid phase that should have very interesting properties. So basically, the name of the game is that you want to look for phases that appear at finite field, maybe above a magnetically ordered phase. And I just want to sort of point you to the fact that this might be a little bit surprising. At least it's surprising to me, because if you think of entanglement, we've heard a lot of entanglement in the summer school. I would intuitively try to imagine that the effect of an applied magnetic field would be to lower the entanglement. And yet, the entanglement probably in a magnetically ordered region is fairly low. And if I imagine some quantum spin liquid sitting above it, then it should actually have long-range entanglement. So the entanglement would have to go up with the magnetic field. And that's a little bit counterintuitive. Of course, the other scenario is just that I kill off this magnetically ordered phase and I go straight into a polarized state. So to me, this reminds me of Reentrant phenomena. If you worked in statistical mechanics, you might be aware of the fact that there's a discussion going on. As I increase the temperature, can I have phases that are more ordered at higher temperature compared to lower temperatures? And this is sort of the same thing, but thinking about the entanglement. I'm not claiming there's any proof here that this is not possible, and in fact, it appears that indeed you can have models with larger entanglement at higher magnetic fields. So we worked a lot on this, and we have some results. And at some point, we decided that maybe we should go back and look just at a slice of this lattice, and that's the Kitev spin chain. So just before we went for lunch, there was a very nice talk on Kitev chain. This is the spin chain version of it. So I have just cut out a row on the honeycomb lattice. And in that case, then the X and Y bond-dependent interactions, that's all I have left. But then, so this model without a magnetic field, I can solve it. That's not a problem. But I want to put it in a magnetic field. And what's different from what you might be used to is the fact that the spectrum and the phase diagram, that's now very much going to depend on the direction that I put the magnetic field. And so the first thing you could do is put the field in the set direction. If you do that, then you can still solve the model, and there's some work from 2008 and 9 or something like this that I forgot to reference, but that clearly shows that if you put the field in that direction, then nothing happens, and you just straightforwardly polarize the spin chain. Then just a couple of years ago, then there actually cobalt niobate here shows results that are indicative in that model or that material might actually be a fairly good representation of this one-dimensional chain that we're looking at here, but in that case, a ferromagnetic version. And what I'll be telling you about here is mostly the antiferromagnetic one. So I need to think a little bit about the field, and so I do the very simple thing. I put in a couple of angles here, so phi for the angle of the field in the xy plane, and then theta when I'm tipping it out of the plane. And almost all I'm going to be showing you today, then the field is never out of the plane, it's just at a 45-degree angle in the xy plane. So that's the plan, and then we hope that this, if we understand this chain here, then maybe it'll tell us something about what will happen if I put two chains together, or maybe try to put 4 of them together and build a real two-dimensional material. Some of the results I'm going to show you are MPS, matrix product states results, and you from the summer school, we all know about this. So the only thing I want to show you on this transparency is that a measure that we like to use for searching for a quantum phase transition is simply by looking at the second derivative of the ground state energy. And that turns out to be a very useful tool. I call that an energy susceptibility, but you could think of it as a magnetic susceptibility or whatever you like. And the finite size scaling of that quantity has been worked out. And if the exponent nu for the quantum critical point is known, then, if it's not too large, then indeed you should see a sharp divergence with the system size. So it's a useful tool, but you should keep in mind that you might actually miss a quantum phase transition. So let me just show you the results, and then we can all go home. So what we first did was, since I mentioned that it's integral for a field in the z direction, then we said to ourselves, let's just put the field in the x and the y direction. If you do that, you can't solve it exactly, and you need to put in a lot of hard work, and then the result of that hard work is that nothing happens in that direction. And by symmetry, also not in the y direction. So again, you just polarize the system, and we were about to go home and forget about the whole thing. And then I said to myself, well, maybe we should check at some intermediate angles. And if you do that, then it actually appears as sort of a strange phase sitting up here. I call it the corn dog phase for the reason that it's sitting on a stick here, which appears to be a critical line. And that critical line there, it's possible to have it due to some symmetry considerations, because there's so-called non-symmomorphic symmetry. I can rotate around the field direction and translate, and then I get back to the same results. So it's possible to have symmetry protection along this line. So we were puzzled by the nature of this phase, and that's what I'm going to tell you about today. And this is one of the peaks there for the energy susceptibility, actually going like this, and showing clearly that there are phase transitions happening. Down in this plot here, I'm showing you the vector chirality. And along this line, it's clearly non-zero. So the phase that appears there is somehow chiral. And then the blue line here, that is the von Neumann entanglement entropy. And you can see, intriguingly, it appears to be very low in this phase. So somehow you could probably get by with some simple arguments that are fitting for simple minds like me. Before continuing, then we did some exact diagonalizations, and I'm not going to explain them in full before the end of the talk. So what I want you to focus on is just the golden points here. That's for a system that has periodic boundary conditions. And in that case, in this phase, it appears that there's a spin gap. If we go over on the other panel, then there are some blue points here, and that's results for open boundary conditions. And that shows that in that case, there's actually a whole bunch of states that come down and fill in this gap. So there's a very distinct difference between open and periodic boundary conditions. Even more intriguing, if I plot the actual energy that you find, then the blue line here, that's for open boundary conditions, and the red line, that's for periodic boundary conditions. And the energy is always higher with periodic boundary conditions. There's one more bond when you have periodic boundary conditions. So usually you would expect that that should be the other way around. So there's something a little bit strange going on here. And so what I'm going to tell you about is what we think is going on, and that's the presence of solitons in the systems. If you want to call them domain walls or kinks or something like this, feel free to do so. But let me tell you what I mean. So if we think about aligning all the spins with the field, then the bond directional Kitev interactions, they're going to be fairly costly at high magnetic fields. So as we lower the magnetic field, we should think about configurations that the systems could go into where the Kitev interaction is 0. And that's very simple to do because I can just consider product states here. So I consider two of them, one where I go x, y, x, y, where I'm just literally putting the spins in the x and the y direction, or I could go yx, yx. It turns out that if I look closely at this very simple Hamiltonian, then I can actually always swallow the field term into the Kitev interaction and write it this way. And if I do that, there's a special field value, which is this one. And at that special field value, then the Kitev interaction of the resulting rewriting, it gives this form. And that turns out that that corresponds to a semi-positive or semi-definite positive matrix. By what I mean is that the eigenvalues are either 0 or larger than 0. And simply by inspection, you can see that these two states that I put in here, they immediately give 0 for the eigenvalues, so it means that they have to be ground states. The other thing I know is that this system should have a gap, but I haven't been able to prove this mathematically, that there's a gap, and maybe somebody in the audience can tell me that this is somehow obvious. But I believe that these two states are actually exact ground states. So if you know about the Majumdar-Ghosh model for the spin chains, it's very reminiscent of that. There are two exactly known ground states, and then you have a gap above them. So if we have two ground states like this, then I can consider topological solitons, which are extrapolating between the two ground states. And I call them chiral also because these states have this chiral ordering that I showed you. So those are the states that I want to talk a little bit about. You can see at a site I here in the middle of the chain, then I aligned the spin with the field. I'm not sort of attached to that. You can consider other kinds of domain boundaries. It doesn't really matter. All that matters is that you're transitioning between the two ground states. and the precise nature of the interface is not really crucial. But if we then go and look and see if this has anything to do with reality, then within this phase, I can simply look at the expectation value of the spin. And what I'm plotting here is just the expectation value of the spin on maybe I should put this one on every second site. And if I do that, then if we look at this one, then you can see that I'm transitioning from x being 0, and then the other end of the chain, then the x here is fully polarized, whereas for the y component, it goes precisely in the other way around. Had I plotted every site, then it would have been a bit of a mess, but you can still clearly see the transition between the two ground states happening. And then as I increase the magnetic field, then I get it into the polarized states, which just looks flat here. And this here is at below the lower critical field, and I'm going to claim that that actually corresponds to a condensation of solitons in the ground state. So this is a little bit counterintuitive, because as you increase the magnetic field, then you're sort of evaporating solitons out of the ground state, which is surprising. So I can plot these, and the simplest thing to do is just to look at the energy density along the chain. And if I compare that to the bulk energy density, then I get profiles like this, where there's a very well-defined kink sitting in the middle of the chain. And if I sum that over all the sites in the system, it gives me a measure of how much the presence of this soliton lowered the energy, and I'm going to call that the soliton mass. And I can trace that out through the system, or through this soliton phase, and that's what you see in this plot here. So it's a sizable amount that we're lowering the energy with by having these solitons present. You can see here I lowered the energy sort of around minus 0.2 by doing that. And the extent of the solitons, you can see it grows with the field. That's what I'm showing over here. When I'm up close to the upper critical field, then they're fairly large, maybe a couple of 100 sites here in the lower plot. And that becomes important. So what we want to do is that I want to try to convince you that this actually makes sense. So instead of these almost exact DMRG results, I'm going to show you some simple variational calculations that we've been doing. So since the starting configurations, that's these product states, I could imagine then building up a subspace that would just have this kink, or the transition, being positioned at any site in the system. And so that's these states that I have here. I call them B states. And if I position the bond, so I start with an X bond here and then a Y bond, then when I'm transitioning from YX to the XY pattern, then the Kitev penalty for doing something like this is actually 0. So there's no penalty associated with this defect. I only lower the energy by aligning the field at this site. So clearly this is a good state to consider, and then I can consider them on every site. So obviously then you say to yourself, well, I put in one of these defects, why don't I put in many more? And then we have to do a little bit more cartoon pictures here, because it turns out that the next defect you put in will then have to transition from the XY to the YX, and that turns out to be incredibly costly. So it's one of the few cases that I know of where the anti-soliton is completely asymmetric with respect to the soliton. First of all, the soliton here, it's present in the ground state. So if you look at the anti-soliton, then the arrangement here of the x and the y, they're opposite of what they are here. So the Kitev terms here will be very, very costly. And that's why I only have one of these solitons in the ground state. So what we can do is now something very simple. This is just to verify that our intuition about this picture is correct. So I just do try to build up a wave function which just has the defect sitting on any site in the system, and then I try to do diagonalization in this subspace. So this is one of the simplest forms that you can do of the variational calculations. They're very similar calculations done by Shastri and Sutherland for the J1, J2 model in the early 80s. At that time, they did everything by hand, which still impresses me today. I don't know how they managed to do that. For the J1, J2 model, it's possible because you have some additional symmetries. But here, fortunately, with the event of NPS wave functions, then I can just work out all these matrix elements efficiently by numerical techniques. And then this gives us a generalized eigenvalue problem that we have to solve, but it's not very big, and you can do that very easily. So the only problem here is actually building up these matrices. And the additional problem is, of course, that everything here is non-orthogonal. So we have to watch out for that. So if I do that, then you can hardly tell the difference. But up here, the solid points, they're actually variational calculations. And in the open circles here, they're almost exact results from DMRG, and there's almost a perfect agreement. And so this is for the soliton. If I do it for the anti-soliton, then I get almost just the flip picture of that. But I want to stress that this calculation here, it would correspond to a state that has very high energy. So I actually can't check that in any sensible way with DMRG. But then the other thing that happens is that so we have this single soliton sitting, and then I can excite it slightly. So the variational calculations, they also give us a number of excited states, and those excited states I can check with the DMRG, and that's what we did here. So I have, again, a wonderful agreement, and you have these beautiful pictures for the excitations appearing in the chain. So the picture is now that the soliton, it has a negative mass, if you like. It lowers the energy, and the anti-soliton has a positive energy. And what I claim is that the sum of the two here should be bigger than 0. That's what defines this phase, and that's what should give rise to the spin gap in the system. And if you look at some numbers, then they actually work out correctly. It does appear that the masses don't cancel out completely. They only do that at the lower critical field, and that's why you get this condensation of solitons that I talked about. So this is a very small gap that actually comes out of these variational calculations. But I can do something a little bit better, because if I'm starting with variational calculations, I can just put in 2 solitons and then do a 2-soliton variational calculation. And that brings me back to this slide. So I now want to explain what the remaining points are here. The red points here, they're actually these 2-soliton variational calculations. You can see there's not complete agreement, but the order of magnitude here is okay. And I would claim that this continuum that you see up here in the exact diagonalizations, they're actually soliton, anti-soliton states that appear not to be bound, but I can't really say anything really specific about that. If you go over on the other side here, then the green lines, they're the excited states of the single soliton that we're getting from the variational calculations. there's not complete agreement with the blue points, which are the exact diagonalizations. So we tried to improve a little bit on it. What we did was that I threw in also the 2 soliton states here, and you could say to yourself, that doesn't make any sense. But since everything here is non-orthogonal, then that actually improves the energy slightly. And so the way to think about this is that it's only for really big systems that the single soliton states here, they really become single solitons. At sort of small system sizes, due to the non-orthogonality, then they're actually being dressed by 2 solitons and 3 and 4 solitons, and then they only emerge from this dressing when I'm up for really huge systems. And you see this because the green lines, which don't include the 2 soliton states here, they actually start to agree once I get up to reasonable sizes. If you remember here, then the size of the soliton, that was maybe 100 sites. So the system sizes that I'm considering here are actually not really big enough, and we should probably continue this work and look at bigger systems. So I'm just going to skip this part because Jose got up, and you can just ask me about this later. Thanks a lot, but I'm not quite done yet because I also wanted to show this paper. So the story, I have never met Chico before this meeting, but I've met his work, and this was about the first paper that I was introduced to as a graduate student. I started up in University of California in Santa Cruz in 1988. And you can see this paper came out in 1988, I believe, and we needed to solve the beta ansatz with twisted boundary conditions. And if you read carefully this abstract, which you can't read, but it has one of the clearest explanations I know of showing how you solve the beta ansatz equations with twisted boundary conditions. And that has actually been incredibly helpful for me in many times in later years. So I wanted to thank you for this paper. And I hadn't miscalculated this. So Saler showed this paper and mentioned that it was almost 45 years ago now. And just sitting around, I was checking, so the number of citations is almost constant. And this is one of the few papers that I know of that are close to 45 years old that still has about 10, 20 citations per year. That is not the case for any of my papers. Okay, thanks a lot.
Thanks. So I would say it's 35 years old, right? Not 45. Okay. I'm not that old. Questions?
It's, yeah, it is 35, yeah. Right? Okay. Yes, it's 12 plus 23. Yeah, it is 35. Sorry, he confused me.
Yeah, go ahead.
Okay, yeah. So let me just. Well, I'm just going to say it. So the point is that when you put 2 chains together, it appears there's a phase that's very analog to this soliton phase, but with sort of much more complicated defect excitations. And so what you might think of is what that leads to when you go to the 2-dimensional limit, which I can't tell you. Yes.
Yeah, how are they connected? The letter is ZZ?
So let's just, I don't think, I deleted a number of my slides here, so this is all I have. Yeah, so it's a regular ladder, and on the rungs of the ladder, there you have the SZ coupling. And so you can think of this as a honeycomb strip with periodic boundary conditions.
But,
And that's the phase diagram we have.
They are matched. The two legs are matched, or you put the x here and the x as well, or
No,
x and
no,
y.
you do x and then above it you have y, and then you go 1 over and it's the other way around.
Oh,
So
okay.
it's literally a honeycomb strip.
So yeah, okay.
I don't call it a honeycomb ladder, because in the literature there's something else that people call a honeycomb ladder, where it's just a straight ladder with peculiar interactions. And then the solitons that I showed you, they now sort of look like what you have here, which I don't know how to do variational calculations for.
Just a small comment, since you spoke about this twisted boundary condition. I saw in your example that the periodic boundary condition has high energies, and actually, if there is some quantum change that this happens, but when you put twisted, your ground state go up to the minimum, and this is the really ground state you have.
Yeah,
it's not the periodic.
Believe me, we've been twisting all the boundaries that we could. So actually, for this simple chain, we indeed put in, we did the whole phi there for twisting the boundaries. And you can see so the minimum is actually for anti-periodic boundary conditions, but I
Twisted sometimes has to be real.
yeah.
The Hamiltonian, but nevertheless, there is some examples like that. Like the biquadratic spin 1 chain happens that. If you compute that.
That's the paper we wrote for. In 1991, that was for the biquadratic chain, where you map it to the spin 1/2 with twisted boundaries. That's why I needed to solve it.
Okay. What are you puzzling you, Adrian?
Okay. We're doing
All right. If there is no further questions, let's thank Eric again. Okay, next speaker, Eduardo Novaes from Federal University of ABC.
Well, thank you very much, Jose, for organizing this seminar, this colloquium and workshop, and for the invitation. And also, congratulations, Chico, for your birthday. It's a pleasure to be here and to participate in one of the exponents of physics right here in Brazil, right? Because it's, was told before, some people here were co-workers with you, but I saw you as a student also and was striving to achieve and to go where you opened the door for all of us, right, like me and Jose. So congratulations and happy birthday. So what I'm going to talk about today is the Hofstadter-Hubbard model. So it's the extended model. So the Hofstadter model is a very interesting model, has a long story. And this is the famous Hofstadter butterfly. But that's not where I started, and that's not why I decided to study this model. So for 15 years now, we've been studying topological insulators for a while. And it's a very exciting area, right? So here is ARPIS, and then you have a conducting band, a valence band, and then you have your surface states. So these topological insulators have been studied and are very interesting for several reasons, and in some areas due to quantum computing, and sometimes just because they are different materials that break our intuition from the symmetry point of view, the usual symmetries. So usually topological insulators are well understood and classified, and here we have the periodic table as it's known due to symmetries, and it's quite old. So this paper, I think it's 2008, this classification. But there are other problems when you start studying topological insulators. And also here you can see that when you introduce impurities in the topological insulator, you're going to find bound states or some chiral states or boundary states also around the vacancies or the impurities. So this can actually lead to a certain percolation and the meltdown of your edge states due to the density of impurities that you have. So this is very interesting, but it's also well known. What is less known is the effect of interactions into your problem. When you do have a topological insulator and you add interactions into the problem. So one thing that is known, and it's known by an example gave by Kitev a long time ago, is that when you introduce interactions, you actually can change the topological phase that you are. You can still be in the topological phase, but in a different one than the no-interacting model that you started with. And one way, actually, to understand the phases that you land when you introduce interactions is to study the stability of your edge states when you do have interactions, when you add interactions into the problem. So that's where I started. And the kind of questions that I want to answer is, what do you do when you introduce the interactions? Do you have measurable effects in the bulk? Not only in the edge, but also in the bulk, right? So as I said, you have this picture of percolation, right, or this melting of the edge states due to a number of impurities and the existence of these bound states. So what happens with these bound states, with these structures, when you introduce interactions into the model? So in order to do that, that's where I go to the Hofstadter model. Let's try to do something that we can control and understand. So the Hofstadter model, it's a model of free fermions moving on a lattice, a square lattice in this case, with a magnetic field. And then you go to the Landau gauge, and it's a very simple Hamiltonian that you can write. So it's a very simple, and it's actually well understood model for the integer quantum Hall state. So this is going to be a small example of a topological phase that we can write down. So if you go to the pi flux, and this is only one possible magnetic field that you introduce, but it's a very simple one because then you end up with a 2x2 system to solve. And there are experimental realizations of this model, especially here in cold atoms. And the reason for that is that why you don't talk about lattice in the quantum Hall model. Usually because the magnetic field that you need to actually see the effects of the lattices are huge. So you don't talk about them usually in condensed matter, but in systems like cold atoms, it's quite reasonable to talk about them. Well, and what about interactions in these models? When you introduce interaction in this model, then you move from a semi-metal to the Mott-insulator phase and actually change the value of the Mott transition, because essentially the magnetic field creates delocalization and try to prevent you from entering the Mott transition. So this is also well known. So the extended Hubbard model, so in the Hubbard model, in the extended Hofstadter model, I have to introduce a nearest neighborhood interaction. Why to do that? Because if you do not introduce next nearest hopping terms, you end up with a direct point, that semi-metal that I was in the diagram before. But when you introduce next neighborhoods, then you'll really open a gap into your system that is proportional to this hopping term for second neighborhoods, second nearest neighbors, right? And this is really the simplest possible topological insulator. You can calculate the shear number, and it's plus minus 1, as it's supposed to be, and it's an easy work to do. You can now write down the boundary states, work on a finite system, and you can solve analytically, and so it's a beautiful chiral state, the boundary that you can write down exactly. So it's a very nice model to work. So now how to introduce interactions, and this is what I will try to address a little bit now. So one of the things is that caught my attention a long time ago is this paper from Duncan Haldane about the quantum Hall effect and the introduction of the idea of spectral entanglement, right? So if you cut your system in half and you look for what are the matrix elements here in the Schmidt decomposition, you can now define the spectral of entanglement as the exponential or number or operator that will give these probabilities here. So in that paper, what Haldane was looking at was actually a spherical system with a monopole in the center, and he was cutting this sphere in half and realizing that in the end of the day, this spectrum of entanglement was reproducing the boundary spectrum. So in the end of the day, even though you're not talking about a system which has a cut, you do have something that resembles the physics of the edge. So why this is interesting, but in the end but what else do you have to talk about is that there is a fictitious temperature that you can think about, which is related to the size of the gap of the system. And then we can call this temperature of entanglement if you want. So beta, which is this temperature, is proportional to this gap. In the extended Hofstadter model that I was discussing before, we can solve this exactly and do the entire calculation. And it's true, it is proportional to the gap, to the inverse of the gap, and you do have your equivalent to the chiral edge states when you do the spectral of entanglement. So this is nice, and it reproduces things that we knew before, and you can go to your continuum limit and write down as a bosonic field theory in your half system, right? And you have your temperature of entanglement. So this is for the no-interacting system, but now we would like to introduce interactions. And the whole point is that this can be done, and what happens is that your spectral entanglement will have a Lagrange parameter, just like you expect for the boundary state of the quantum Hall effect. Right? So this is the idea, and it's consistent with work that was done in quantum Hall problems, where you cut your quantum Hall system in half, and you do have the spectral entanglement reproducing the conformal field theory of your edge states in the conformal model. So now that we do have that, and we go back to the problem, we would like to probe the system, the bulk system. And to do that, I introduce a resonant level model in my model, in my system. This will be my impurity. So with no interactions, without the hybridization with band, this is a flat localized state. But now we can go and ask ourselves, what happens when you introduce the hybridization between your resonant level model and your system, right? When your bulk system. And in the end of the day, the idea is that, well, you can trace half of your system passing through the impurity and write the spectral entanglement of the model there. And as I said, this will end up being a Luttinger liquid model passing through your impurity. And you're going to have the interaction between this Luttinger liquid and your local levels. So all the interactions in the bulk inside this gap phase are now masked, is all accounted for inside the Luttinger parameter in the spectral entanglement. So, oops, sorry. So now that you do have that, you can use all the tricks that you want, but work at a finite temperature. What finite temperature? The temperature of entanglement, which corresponds to the bulk of the gap, the gap of the bulk. So you can do your RG, cut your RG at the size of the gap, and then understand what is the physics that your resonant level model do have here. Oh, I'm trying to, your resonant level model will have here. As we all know, we're going to have a Kossler talus, we're going to be sitting in the no-interacting model here, and for attractive interactions, we are going to be in the overdamped regime. And that's exactly what we find. We'll go to this RG flow. You can cut at a certain temperature, which is the gap. For no interacting system, this can be done exactly. And as you see, there is no interaction here and no relation with the gap. So it's just proportional to the fermionic bandwidth. It's temperature independent. But now when you introduce this is a Habi oscillation that we are looking at. This is one particular observable that you can look at. And if you do the same calculation now with your interactions, you see that now you do have the spectral entanglement here, and you also have the Luttinger parameter showing up on the overdamped, what will be the Habi oscillation. There are no Rabi oscillations because you're in the overdamped regime. So what happens in the end is that although we cannot, using this spectral entanglement, we can use everything that we know about Luttinger liquids in one dimension, but working in a two-dimensional model. So, and looking at the physics of interactions on these systems. So that's the general idea, and I hope that was an interesting introduction to this topic, because we always want to go forward with things that we know. And we know quite a lot about one-dimensional systems. So how we can move forward to two-dimensional systems and move some of the knowledge that we do have to two-dimensional systems, to one-dimensional systems, to these two-dimensional ones now. So that's it. Thank you very much. And I hope happy birthday to Chico.
Thanks a lot.
Right on time, huh?
Sharp on time. Questions, comments? So that was just for one impurity. What's your feeling when you put many impurities? Are you going to have a localization?
This crosstalk, that's the thing that I'm working now. So the thing is, now you can, if you have two impurities, then you can cut the system and write the spectral entanglement connecting the two impurities, and you're going to have just like when you do impurities on the edge of your topological insulator. Now you're going to have your impurities talking through these Luttinger channels, but they are cut by the gap. So in the end of the day, what people taught you when you were in grad school was true, right? So you can replace temperature and gap almost without thinking too much about it. So, but that is a kind of a justification for that.
More questions? There is a controversy in the literature if the Chalker-Coddington model, which is the one semi-classically used to explain the integer quantum Hall effect, doesn't really match with the exponents measured in experiments. Do you have any comment with that, or
no, not
do you
really.
think that going through this lattice model, you'll be able to capture things that the Chalker-Coddington model doesn't capture, or
No,
the co-pretty interactions?
I really don't know how to address that. I never studied this. But as far as I know, this lattice model has a lot of things that you do not expect in the traditional Luttinger quantum Hall model, right? Especially because you are working with this very large magnetic field. But why this model is very important in physics? It's because I think it's the best way to control the commensurate and incommensurate transition and to understand it. As you change the magnetic field, you go to several incommensurate phases, right? So that's why people started looking at this, I think. But I don't know if there is a connection, a real connection with the integer quantum Hall.
Thanks a lot.
All right, thank you very much, guys.
If there is no further questions.
Essa água aqui.
Pode beber.
Ai, eu sou a última pessoa. Vou pegar essa aqui. Vou voltar a câmera. Está aberto. All right. Are we allowed to start early? No. Tem 2 minutos, sim.
15 minutos mais 2.
Okay, next speaker and the last of this session before the coffee break. Teresa Mendes from
Representing the house.
Yes. Please,
Thank
Teresa.
you. Okay. So I realized I called it a lattice affair because it's, I think, the thing that's very shocking about the way you do treat quantum field theory by putting it on a lattice. But of course, in almost talks you've heard have lattices. So what is the connection between non-abelian gauge theories and statistical mechanics, or why do I allow myself to infiltrate this event? Since my research is with quantum chromodynamics, which is the theory explaining the behavior of the strong nuclear force, or how it, affects quarks and gluons. So that reason is because I feel very strongly connected to statistical mechanics, and that is the reason that I came to live in São Carlos 22 years ago. And that's because I knew about São Carlos from when I was a student, And when I first started graduate school and in my master's studies, I was studying statistical mechanics, and I was from the daughter institute in São Paulo, from the University of São Paulo in São Paulo. And there was just no question that the best place for statistical mechanics was 200-something kilometers from São Paulo, and it was here. And there was quite a lot of interesting, exciting activity. So, you know, I knew I had to come here when I was still an undergraduate, but there was some really important statistical mechanics school, and I just came. And, you know, couldn't believe that all those important international people were here. They would never come to São Paulo, but they came here. So that's why I knew São Carlos was a very important place for statistical mechanics. And in fact, there's a connection with the way that we study QCD. So you just have to take my word for it for now, but I'm very happy to participate and to pay, you know, my respects to Chico, to Professor Alcaraz, because of his contributions as a researcher and as a teacher. I'm enjoying the school and the workshop. The school I couldn't really attend a lot. I just came on the first day, but the workshop, the fact that you can follow from YouTube has been really nice. Of course, I'm very busy because I'm the head of the undergraduate program now, and there's a lot to do. But there's also, you know, in this capacity, I appreciate very much the contribution of Chico as a teacher. And I realized this only, you know, maybe recently. The reason, you know, then I got into working with lattice QCD and lattice gauge theory. Many, many years ago, there was a lecture course, and somebody had the book, and I made copies of one particular course, and it was by Chico. So I'm very sloppy. I was supposed to look through my things and get my copy. I didn't, so I just got this online. It's from IFT from São Paulo, someone from the library, but I have mine in my office, so I don't know if you can read it, but it says here, Alcaraz, and it is teorias de calibre na rede. So nowadays we just say teorias de gauge na rede. We just gave up translating the word gauge, but back then I think it was very important to use the correct word. So that was the school in '81. I wasn't a student in physics yet, but then somebody had left this book. And I just find it funny because and this is a very traditional school for people who don't know. It's a particles and fields school. It's Vieca school every 2 years. And there's one coming up because it's every 2 years. But the previous one, I was in charge of the main organizer. And I thought it was very nice because since it was virtual, it was online, it wasn't really anywhere. And of course, Vieca was from São Carlos. It was very important to quantum field theory and theoretical physics in general for Brazil. But I don't think the school was ever in São Carlos. I don't know. It's usually, you know, a more touristy town. But this one was online, so we just pretended that it was in. This one was the first. Oh, okay, great. Yeah, obviously, this was the 20th school. Okay. That is really nice. I mean, that's Vieca there, you know, I think it was probably at the UFSCar. But, you know, since it wasn't anywhere and the three organizers were from Niterói, Salvador, and São Carlos, we just used pictures, you know. Actually, well, okay, won't extend it too long. And then these are pictures, you know, from the places, and this is the picture of the important citizen of São Carlos. So, okay, too much because I know I only have a few minutes. So try to convince you that there's a strong connection between what I do and statistical mechanics. Gauge theories, and that's why when you talk about a lattice for quantum field theory, it should be very shocking because it has to do with, you know, butchering the space-time properties in a very significant way. But, you know, just before we start, gauge theories, and we don't often think about that, but they arise from when you impose a constraint that there will be invariance of the fields and the Lagrangian. by some symmetry. And this is a very strict constraint. And so it's not surprising that a lot of very drastic properties will come as a result. For electromagnetism, we know, it's just by a rotation and it's a gauge, and you choose a gauge and there's a convenient gauge and so on. But maybe because it looks, it comes so easily and it looks so harmless, we don't really think about what it means, but it's really, really messed up. I mean, it's, the system is forced to be symmetric under rotations, arbitrary rotations in every point. Okay, so it is a very strong constraint, and it's there. You just kind of take it for granted. And it's even more restrictive when you go and ask that this symmetry be non-abelian. So U1 is a rotation. It doesn't matter the order that you do 2 rotations. But if you do it for a matrix and still ask your fields and your Lagrangian to know nothing of the physics, will know nothing about this crazy transformations, weird things come out of this theory. So in particular for QCD, which is a non-abelian case, or Yang-Mills theory, Yang-Mills Lagrangian, it is believed that the fact that you have forced this non-abelian symmetry on your system, on your theory, as a result, you will never ever see the particles naked, with the naked eye. So all your fields, all your particles will be confined forever. And that's, in fact, how we explain why we have mass and why, the nucleus is the way it is, the protons glue to each other, and the neutrons also, and so on. And inside these nuclear particles, you have the real fields of the theory, which are quarks and gluons, but they'll never come out. We would like to understand why this is so. Nobody does. And it's a question of confinement, and it's an important question. But how would you, assuming that you have the right theory, and you do, because in another limit you can do perturbative calculations, and the QCD is the theory for the strong interactions, how would you study this, and how would you investigate how this arises from the Lagrangian, like from the theory? And that's where the lattice comes in. So it's an important theoretical problem. You might say, if you're a little pretentious, that it's the only last problem left, theoretical one from the standard model. Because this is not anything new. It's part of the standard model of particle physics. And you want to describe this feature, but it is a non-perturbative feature in the low energy limit. And this answer, this magical method to study it without throwing away, important parts of the theory. So you don't want to do perturbation theory that works so well for QED, for example. And the way to do it is to regularize the theory on the lattice. Okay. And who came up with this brilliant idea? Kenneth Wilson. So I don't think I want to go into too much detail, but if you look at the Lagrangian for QCD, it looks just like the one for QED, identical actually. It's only these little things here. These are extra degrees of freedom that have to do with the fact that you have a more complicated symmetry, so you have an extra, you have a different kind of charge. Instead of the electric charge, you have this color charge. So your fields have this color index related to that charge. And your field tensor has an extra part, so it's not only the one from electromagnetism, but it has this thing, and that has to do with the fact that you have non-commuting fields. You can think of this as the vector potential, for example. Okay? And this thing that I painted red is nonlinear, because then when you have F mu nu, you won't just have quadratic terms, you will have higher orders, and then this just makes everything extra complicated. So the thing that you want to study is also the thing that doesn't let you study it by the methods that usually work in quantum field theory. Very similar to QED, but has this crazy feature that in the end your gauge bosons, which are the equivalent of the photons, the gluons, and there's a good reason to call them that, they also carry the charge. They also feel the charge. So they attract each other, they interact with each other. You can have, in the Lagrangian, when you have something that's a vertex, you see that there's some interaction. It's not just a propagation. So you have a 3-gluon vertex, so interaction of 3 gauge particles. You have 4-gluon vertex. It's a whole mess of things. And that's highly non-perturbative, non-linear, and then therefore you have this disadvantage that it's non-perturbative. Okay? And then non-perturbative here means because roughly, if you think in terms of the hyperfine constant, and it's something that's small, and you can do perturbation theory with Feynman diagrams and expand because it's small and you have orders of this. For QCD, this intensity of the interaction is only small in some limit, but not in the limit of low energy when you want to understand the bound states and why the proton is the way it is, why it has the mass that it has, and so on. Okay. So you have these 2 regimes, the asymptotic freedom, where you have small constant, coupling constant, and in the other end, you see you have models to try to explain that you would have that the gluon field forms these flux tubes and so on. Of course, if you, and then this is thought to be of the same kind of potential as a string, so when you pull them apart, the potential rises linearly. So you would really like to understand how this can be obtained from the Lagrangian. And then, of course, if you pull and then there's enough energy that's stored in the field, you will have a creation of a new quark-antiquark pair. So, in fact, the string breaks, but it breaks in a way that you still have confined particles. And this is to understand that this coupling constant is not constant, and it changes, and when you go to lower and lower energies, it gets very high. So there's no hope that you can do this, the same kinds of perturbation perturbative treatment that you do for example, QED. And then, what's a brilliant idea that came, and, this paper is, last I looked, but I'm pretty sure it is still. It has a lot more citations than the Nobel Prize papers by Wilson, the normalization group, and it started a new field. This is the field that we work in. So this is work in collaboration with Attilio Cucchieri. He's not here, but he may be watching on YouTube, so I want to make sure I mention this. It's our group here at the San Carlos Physics Institute. And it's really a beautiful paper because what he does is he defines this lattice version of the Lagrangian and the field theory, and he solves or studies it doing something that is really statistical mechanics, because the strong coupling expansion is a high temperature expansion. Very nice to prove, in some way, in some limit that you have that linearly rising potential. So I don't know, maybe this is not, I don't have time. This is really nice because 30 years later, he reflected, what that meant and how he came up with this. And then he says, I thought this was really exciting back then, and I didn't know enough, that's what he claims, to start in this new exciting field of quantum field theories and the gauge, non-abelian gauge theories and so on. So he said, what I knew was statistical mechanics, so I just thought of a version, lattice version, and a statistical mechanics version of the theory. Okay, so 30 years, what is brilliant and, what might, why is Wilson his idea so special is that obviously when you have the quantization from path integrals, you already have this idea that you have weights and you have different configurations, so it's already looking like statistical mechanics, but the weights are, they have complex numbers, and so if you think you changed your time variable to be a pure imaginary number, then your weight becomes a Boltzmann weight or Gibbs measure. So that's true for any formulation of the theory, and you need to do this anyway. I mean, quantum field theories is sick in the sense that there's ultraviolet divergences, so you need to do some regularization process and then think about, the renormalization, which is a non-trivial step also. So it is a lattice model like so many of the models that you've seen here, but it's a very dangerous one because you have to then make sense of what happens when you remove this spacing. But while you're studying and you have this is something you would have to do anyway. You have to regularize anyway. There's other ways of doing it. This is just very beautiful, very mathematically robust, but it just looks hopeless to treat it because it then becomes a extremely complicated statistical mechanical model. And the lattice spacing gives you what you need, this ultraviolet cut. But what was very brilliant of his, for Wilson, and then of course if you're going to do it like we do, like you have to do, going to study it on a computer, then you also have a volume cut, and that's an infrared cut. But the proposed action is something very elegant, very beautiful, because if you think in terms of symmetries, and that's what's really important in quantum field theories, you're butchering many of them, like the rotational symmetry now is 90 degrees, and the translation is in units of this lattice spacing, but the gauge symmetry is preserved very nicely. So it's written in terms of these oriented plaquettes, and that you can find in Chico's lecture notes explained why this is a great idea, and then you build up this observable, the Wilson loop, and then you get from this famous linearly rising behavior, but then that's not really what you want because you want to show this in the physical limit, and the physical limit is when the lattice spacing goes to 0, and then, supposedly Wilson was very depressed because this was not, there was no indication that even, expanding in the analog of the high temperature expansion you would get anywhere, and you won't get anywhere. And you had to do this numerically, and then how do you show that you're close to the scaling limit that you need, and so on, But many decades later, and then of course the way to do it is using lattice Monte Carlo simulation, which is common in statistical mechanics. And it's really hard, the simulation is really heavy, and so on. And it's very nice that you can get these pictures nowadays, and also for a few years already, that you can see the predicted thing, the effect of having this confinement, which is the flux tubes. This is for a pair of quark and anti-quark, and this is for 3 quarks, so for the proton, for example. And you can even see, the linearly rising potential and the breaking of the string and so on. So people were, if you're from this community of lattice QCD, you're happy to say that, it's under control, we understand it, but we don't understand it, we see it. So seeing is not the same as understanding. And we know what it looks like, but do we really know what it is and what makes it come about, this behavior and so on? And then, there's a whole lot of people who study this. And if you're very good and you are able to understand this in a mathematical way, there's $1 million for you. It's one of the Millennium Problems. Well, 1 minute, good. So that's a brilliant idea by Wilson. Do we have also some brilliant adjacent contribution from our group? So what we use, and there's different ways to try to understand confinement. What we use is this last one, which is a confinement scenario that's based on 2-point functions, not only of the gluon, but also of the ghosts that appear when you do this gauge fixing. And there's theorems and attempts to understand this geometry of the configurations and so on. This scenario is about a gluon propagator that goes to 0 or that gets suppressed in the infrared limit, so when the momentum goes to 0, and then the ghost is something that will feel the confinement and respond very strongly to this low energy limit or long distance. And then, people had predictions and, analytic results and so on. And then there were also a few crazy people who did this numerical simulation. So this, when we started, we came here, and this was work also before, but this is what we concentrated on for a few years. This is not important. Technical things. One technical thing, very nice, is that you don't really have to consider the QCDKs, which is an SU3 group. You can look for the same behavior in SU2. case, and you don't need to consider the fermions for this. I mean, you can, but it's not really what you want to test. So then issues, and this is main issue here, is that you have to really invest in going to the large lattice limits, and how do you do this, and how do you, keep things under control. So these three things is what we did. So we tried educated guesses for the infinite volume behavior. We tried, out-of-the-box thinking, how to study this geometry of the configuration, the region of the configurations. And then this was really more like a condensed matter idea, thinking of periodic crystal to represent the lattice. Just go over very quickly all the results that we had. This is rigorous bounds, rigorous lower and upper bounds for the gluon propagator and zero momentum and so on. And then it turns out that lower and upper bounds are telling you what you should have already thought, that when you're summing the things and it's just 2-point functions, it looks a lot like a susceptibility. So it will have a behavior like 1 over square root of the volume, and we just saw that this was so. And this was something that, in the end, allowed us to go to these very large lattices and have control. This was a very shocking paper for this community in 2008. We did the same for the ghost. We did some things in this exploring the boundary of this region. And this is the one I was mentioning, of reproducing the lattice, like cloning the lattice as if this was crystalline potential, and then doing gauge fixing and studying the gauge aspects, gauge-related aspects, and the gluon propagator for this fake lattice, and showing that you really get almost a free lunch. You just don't have all the points. The green one would be like doing the brute force thing. And that's it, bro. So Netta won't be mad at me. So summary, I'm talking about a way to study non-abelian gauge theories that is non-perturbative, is very powerful. It's based on lattices, and it's something that I usually say that has pixels and bytes, because it's also something that you have to do numerically. And it's all based on statistical mechanics properties. And the ideas that I showed here, our ideas to go to this very large lattice volumes, I only realized this now. I mean, they're all exactly ideas to take better advantage of the statistical mechanics properties of lattice QCD. Thank you, and sorry for being too long.
Thanks a lot. Thanks for showing that we do condensed matter even inside the atom. Okay.
That's not what we showed. We showed that you can do particle physics and still publish on Physics Rev Letters. If you...
I have questions that are from a complete layman in the area. First of all, do these calculations give you the value of the mass cap of the clay problem?
Yes.
Okay.
The problem is, for that, you really need to have a mathematical idea of why you get it. But this has been true for, actually, that year, 2008, is also the year that people from this community consider that finally the first really reliable calculation of the mass of the proton was done. And they were very clever, these people, but then they have really big machines, and then they take into account all the really physical parameters, so they have all the quarks, the fermions, the things there. These days, they even include the electromagnetic effects. But back then, 2008, they published this thing, and they were very clever, so the press department of, I don't know, the university or something, that sent it to newspapers saying, physicists proved that Einstein was right. Because, you know, it's like energy becomes mass. Because this is really, it's massless gluons and almost massless quarks, and then they get together, and they're something that only 1–2% of the mass is really mass from the Higgs boson or something. Okay. So it's, the vacuum creates our mass.
But the smallest gap in the clay problem is the glue ball, right?
Yeah, which has not yet been confirmed. Right? And if you do what we do, that's what you would be honestly looking for, because, you know, you're not considering the fermions.
And the other hadrons, how does the calculation fare in terms of experimental values? Proton, neutron.
Today, you would say that light hadron spectrum is perfect. Actually, the lowest one is the pion, because it should be ghost symbols and should have 0, but it has a little more than 0, 130 something, 38 MeVs, and then you can do this. What I didn't show, of course, I mean, it's the very non-trivial thing. After you've done your very complicated lattice model, you still have to connect it to the continuum. So you have to do renormalization to get the physics. And to do that, you need to pay something, so you need some inputs. So it depends if you use some masses or not. But that's even something that at the beginning, like turn of 2000, around the year 2000, people, if you use different inputs, you would have different results for the spectrum. All of that is under control now. There's no issues, even, chiral symmetry. It's gotten really, really sophisticated, but we still don't have an answer that is worth $1 million for the first problem, because Wilson's paper was confinement of quarks. And we still don't have a very good answer to where does that come from, from the fundamental aspects of the theory. And I don't know, maybe I'm just venting. It's a little frustrating. It's a lot frustrating, I don't know. But it's come a long way, absolutely. And now experimentalists, they come to lattice people and ask for, where should I look for, for new particles? And there's particles that have been predicted first from simulations. And
so thanks for a fascinating talk. My question is, since the early days of lattice QCD, in the StatMech community, all sorts of tricks have been invented to improve the efficiency of Monte Carlo, such as sample reweighting and entropic methods. And I'm wondering how much of that has been adopted by the lattice QCD community.
Great question. Thank you, Ron. I don't think, most of the people in this community do not come from statistical mechanics, are not really paying attention to developments and so on. But no, the reweighting, I think, is really a wonderful example. And then the special kind of reweighting that's even better is proposed by a Brazilian. And that, I didn't even know about that because, it was after I had started studying field theory. And then I learned that I was from Paulo Murillo. But the people who work with finite temperature QCD, they know more because it's QCD thermodynamics and, But, occasionally you have these bizarre conversations like, a critical exponent, and then they were looking for an inflection point to determine what the phase transition was and this kind of thing. So it should benefit a lot more from statistical mechanics, but it's what it is. It's statistical mechanics, and it should, do its homework and look for results. And, I think we did some things like that. Like if you're from, just the last thing I'll say, if you're a field theorist and you're computing things, you're looking for expectation values and, vacuum expectation values and so on, you're looking for a number. It's a huge integral, and you take an average and so on. But we are doing the same. But we're taking the long way because we're producing the fields. I mean, we're sampling them with the right weight and so on. Are we extracting all the information we can from these fields? So that's one thing we started doing, is that we have all the fields, even the ones we can walk around and look for the ones, the neighbor ones that are not representative in terms of the weights and so on. So I think there's a lot to be done that has to do with how we study the quantum field theory, and that maybe other people are not aware of it.
Thanks a lot, Teresa.
I'm sorry, And I didn't say happy birthday to Chico.
It was very nice.
Thank you.
So thanks, Teresa, and all the speakers of this session. We resume at 4:30. Angela,
Oi.
can you hear me?
Yes, I can hear you.
Good. Can you put full screen mode, please?
I think it's already.
There is still lots of space to go.
And now?
Yeah, it seems okay. Maybe Michael, parece que tem pouco da tela tá. Okay, it seems that it's in our side. Just a second. It's fine. You're set, Angela.
Okay.
Okay. The session starts with Angela Foster from Rio Grande do Sul. Angela, thanks for virtually coming. It's all yours.
Okay.
You have 30 minutes.
Okay, first of all, it's an honor and a pleasure to have the opportunity to give a talk here to celebrate the 70th birthday of Professor Francisco Alcaraz. I thank the organizers very much. First of all, happy birthday, Chico. I wish you all the best, lots of love, peace, many, many more healthy years. Yeah, I'm so sad that I couldn't come in person. Actually, I had everything ready and prepared. The luggage was ready. And I got sick the night before, and I have to cancel everything. But anyway, I still have a present for you here that I would bring and give to you. But we have to leave this for the next time. But anyway, let me also thank you for being a huge inspiration for me and for many scientists, for many different generations. You could see today in the talks of Juliano Ribeiro, Eduardo Novaes, Teresa, everybody were touched by your work. So you have a collection of important works. I'm here just showing a few of your beautiful works. Works are the reaction diffusion processes, conformal invariance, correlation functions, entanglement, and much more. So these are all relevant contributions to statistical mechanics and integrable systems. And talking about integrable systems, this is what I'm going to talk about, integrability, more specifically, the design of integrable quantum devices. So my talk will be divided in 5 parts. In the introduction, I will briefly review some experimental results that will motivate the study of integrable bosonic quantum tunneling models. We had in this afternoon also a nice talk on tunneling models, tunneling. As an application of these models, we will discuss and show how an integrable triple L model can be used to construct a switching device. And as a second application, I will show how to use an integrable 4L model to generate a null state. And in the conclusions, I will present a brief outlook of the results. So let me begin by showing some experiments that motivate the study of these models. The first experiment was performed by the group of Markus Oberthaler at Heidelberg, where they did a direct observation of tunneling and self-trapping in 2 condensates, in 2 weakly linked Bose-Einstein condensates. So we have 2 L's, and they studied what happened with the density of atoms, here in red, along the time. So this is the time of flight. Depending on the conditions, the atoms, they can tunnel between the wells, or they are trapped in one of the wells. So an experimental realization of tunneling and self-trapping was realized by the group of Markus Oberthaler. And in the next section, I will present an integrable model that describes qualitatively tunneling and self-trapping. Okay, still in this quantum tunneling context, a triple LBC transistor was proposed by the group of Dana Anderson at Chile. So the proposed device consists of trapping a BEC in 3 specially separated wells, the source well, the gate well, and the drain. And they show that under certain conditions, the atoms in the source can quantum mechanically tunnel to the drain via the gate. So transport dynamic of cold atoms was experimentally studied in this triple LBC transistor. And like an electronic transistor, this device shows a switching behavior. And in section 3, we'll discuss an integrable triple well model that exhibits a switching behavior. Another important experiment was generation of null state by the group of Peter and Michels at Stuttgart, where they have succeeded to generate high-quality null state using focus, allowing through a supersensitive interferometric measurements. And in section 4, I will show how to use an integrable four-well models to generate Bose-atom null states. Okay, so far for the motivation. Let us now study bosonic quantum tunneling models. So the first model that I want to present is the simplest one, the case of two wells, the two-side Moss-Hubbard Hamiltonian here. So the Hamiltonian is given here. We have two wells and one atoms in well 1 and two atoms in well 2. The standard notation that A1 destroys an atom in well 1, A1 dagger creates, and so forth. N, which is N1 plus N2, is the total number of atoms, which is conserved. So in this model, K is the atom-atom interaction term. Delta mu is an external potential. It measures the asymmetry between the wells. And epsilon is a coupling for the tunneling of bosons between wells 1 and 2. Although very simple, this model exhibits important and physical behavior. If we study the quantum dynamics, we can see clearly that it exhibits tunneling and self-trapping in qualitative agreement with the experiment of Marcus Oberthaler that I showed before. Now I want very shortly and briefly to show that this model is integrable, that it has a Bethe-Ansatz solution. For this, I will consider the algebraic Bethe-Ansatz method, make a connection with it. In this construction, we have basically three ingredients. The first ingredient is the so-called R matrix here, this 4x4 matrix, with elements 1, B, and C here. U is the spectral parameter. We can show that this R matrix obeys the Yang-Baxter algebra. So this is the first ingredient that we choose. There is a second ingredient, which is the so-called monodromy matrix, T. The elements are also matrices. And we have to choose this monodromy matrix in such a way that the Yang-Baxter algebra for the monodromy matrix is obeyed, this RTT relation. Here, in this case, we will choose the following realization of the monodromy matrix, written in terms of these L operators, written in terms of this Heisenberg algebra. So, and then we can show that this choice obeys the Yang-Baxter algebra for the monodromy matrix. There is a third ingredient, which is the transfer matrix, defined in the usual way as the trace of the monodromy matrix. Then, using this Yang-Baxter algebra for the monodromy matrix, we can show that this transfer matrix commutes for different spectral parameters. So the model is integrable. And what is the relation between this algebraic construction with transfer matrix and the Hamiltonian for the two-side Moss-Hubbard model? We can show that the two-side Moss-Hubbard model can be constructed from the transfer matrix by this relation, the first one. If we do the following identification between the elements of the Hamiltonian, these parameters, atom-atom interaction strength, external potential, and tunneling, and the parameters that appear in this algebraic construction. So if we manage to solve the eigenvalue problem of the transfer matrix, we will also find the spectrum of the Hamiltonian. We use then the algebraic Bethe-Ansatz method, and in the end of the day, we do the calculations using the Fock vacuum as the pseudo vacuum. We end in these energies here. The VIs here are solutions to the so-called Bethe-Ansatz equation. Each set of VI solution to this equation parameterize an eigenvector with this energy. We have many solutions. One is the ground state. We also have elementary excitations and so on and so forth. So this is the Bethe-Ansatz solution in a nutshell. And similar strategies can be employed to construct integrable generalized model in this quantum tunneling context by exploring different realizations of some algebras. We can use different representations. We could use another realization of the monodromy matrix or even other R matrices. As long as the Yang-Baxter equation is satisfied, we will be able to find integrable families of models. A short remark, it was believed until very recently that it was not possible to construct integrable multi-well systems, such as integrable 3 wells, 4 wells, And in fact, the algebraic construction for these models is more complicated, and there are some tricks to get all conserved quantities. But in the end, we managed to construct integrable triple well, integrable four wells, and integrable multi-well tunneling models that I will present next. So this is the Hamiltonian for the integrable triple well model. So we have 3 wells and 1 atom in well 1 and 2 atoms in well 2 and 2 atoms in well 3. They're using the same notation as before. The total number of bosons is conserved. This Hamiltonian is invariant by interchanging the indices 1 and 3. And here U is the parameter that controls on-site and interwell interaction between the bosons. And the T's are the couplings for the tunneling of bosons between wells 1, 2, and T3 between wells 2 and 3. So this model is integrable for any choice of the parameters. As before, we can use the same R matrix and another realization of the monodromy matrix to get transfer matrix and connect it to this Hamiltonian. We can find the Bethe equations and so on. I'm not showing this here. You can see later. I can show you later if you are interested. We can also construct an integrable 4-well ring model. So here we have 4 wells, 1, 2, 3, 4. Again, the parameters U controls on-site and interwell interactions, and the T's are the coupling for the tunneling of bosons between wells 1, 2, 2, 3, 3, 4, and 1, 4. In this case, the T's are not totally independent. There is a constraint, the product T12, T23, T34 must be equal to the product T23, T14 to assure integrability. But even with these constraints, we still have a lot of freedom to investigate a range of anisotropic regimes. As before, we can also obtain this Hamiltonian from a transfer matrix using the same R matrix and another realization of the monodromy matrix. We can find the Bethe equations and more. These results can be generalized for Hamiltonians for n plus m wells. Here, written in terms of sets of canonical boson operators, A and B. We have the same notation as before. And these models, they are defined on complete bipartite graphs. For specific choices of n and m, we can recover existing models or we can find new ones. For example, by choosing n equals m equals 1, we recover the two-side Boss-Hubbard Hamiltonian. By choosing n equals 2 and m equals 1, we obtain the integrable triple L Hamiltonian that I showed before. By choosing n equals 2 and m equals 2, we obtain the integrable 4-well model that I showed before. And by choosing n equals 3 and m equals 1, we obtain an open 4-well model. Just observation, here we are using the schematic representation that the spheres represent the wells and the bonds indicates the tunneling between the wells. We can also obtain, for example, an integrable 6 wells. By choosing n equals 3 and m equals 3, we can obtain another 6 well by choosing n equals 4 and m equals 2 here. We can obtain an open integrable 6 well by choosing n equals 5 and m equals 1. Okay, so far we have introduced this family of multi-well tunneling models. Now, in what comes next, I want to find applications of these multi-well systems. First, for the case of the triple well. So we want to study an application of the integrable triple well model, how to use it to construct an atomic switching device. So here we have, this is the integrable triple well model, the same model that I wrote before, the H0. So we have the 3 wells, again with the same notation, and 1 particles in well 1 and 2 particles in 2. And 2 particles in well 3. The same notation as before. U controls on-site and interwell interaction, and the J's, the coupling for the tunnels. So this is the integrable Hamiltonian. And now we want to break the integrability by adding a term like this term here, this epsilon term here, epsilon n3 minus n1. This means physically that we're applying an external field, and these are doing a tilting in the wells. So now we have these two regimes. In the integrable regime, where epsilon is 0, there is no external field, then in this case, the model is integrable. So the model has 3 modes, so 3 independent conserved quantities are expected. They are the Hamiltonian, the total number of particles, and this conserved charge Q here. So we have these 3 conserved charges, independent. And the other regime is when I apply the external field, epsilon is not 0 anymore, then this conserved charge Q is not a conserved charge anymore. We don't have this commutation relation anymore. So now, in what comes, I want to study the quantum dynamics to probe the conditions under which a switching behavior can occur. And here switching means the capacity to effectively block tunneling in a particular well. For this, we will study the quantum dynamics, first for the integrable case and after for the non-integrable case. So we have here the time evolution of the expectation value of the number of particles in wells 1, here the source in pink, well 2, the gate in cyan, and well 3, the drain in blue. We are using the initial state 60, 0, 0. All particles are in well 1. We choose, we make this choice for the J's. So we fix J, we fix the external field 0. This is integrable regime, and we will vary the interaction parameter U. Each figure is for another U. What we observe here, by increasing the interaction parameter U, A, B, C, D here, what happens is that increasing U leads to a decrease of the tunneling into the gate until we reach this final situation where the tunneling in the gate is negligible, and we have an important feature that we have oscillations between the source and the drain here, which are very close to being a harmonic and coherent. And in this last figure, we have the situation where the tunneling in the gate is switched off. We have a resonant tunneling regime. And this last figure is very convenient. It is a very good starting point to investigate non-integrable dynamics, using this parameter epsilon, this external field, to control the tunneling of bosons from the source to the drain. So here we have again the quantum dynamics, the time evolution of the expectation value of the number of particles in well 1 in pink, well 2 in cyan, and in well 3 in blue. Now we fix the parameter U. We fix U, it's the same parameter of the previous last figure, the same values of J, and now we vary the external field. The first picture is for the integrable case, where we have a switch-on configuration with maximum tunneling amplitude between the source and the drain, here. And then by applying the field, by increasing the field, we have a decrease of the tunneling amplitude here, and we have basically just 30% of the original amplitude. In the first case, in the original case, we have a switched-on configuration with maximum tunneling amplitude. So here the amplitude decreases until we reach a switched-off configuration. And we have a control of the physics in this resonant regime. Here we have in the last figure the tunneling amplitude and the tunneling frequency in the inset here as a function of the external field. And we can find analytical expressions for the amplitude of oscillation and for the frequency in terms of our parameters. And these analytical expressions, they give very good agreement with results obtained by numerical diagonalization. Here we present a comparison between analytical and numerical results. Here in the first figure on the left, we have the period as a function of the external field. The orange line shows the period from the analytical expressions compared to the numerical points, which are the green crosses. And on the right, we have the dynamical evolution of the fractional occupation in well 1 as a function of time and external field. And also here we find a very good agreement. Some remarks. surprising feature of this result is that the ability to control the system in a predictable way in this resonant tunneling regime arises by breaking the integrability. And this level of control points towards the potential use of a physical realization of the model as a quantum switch. And what about the feasibility of a physical realization? As you all know, when we try to publish an article, they have always asked us, so can you say something about the possible feasibility of a physical experimental realization of the system? This happened also to us. So to investigate the possibility of a physical realization of this theoretical switching device, there is a long story. The first step is to make a connection with a work of Chilman-Fao and Luis Santos and La Haya, where they study an extended three-side Gauss-Hilbert model. Basically, they study this extended three-side Gauss-Hilbert model here, what we have here. So in particular, our model, our integrable triple L, is a particular case. It is related to this more general Hamiltonian that models dipole-dipole interactions and tunneling between adjacent sites for dipolar bosons with large dipole moment, such as chromium and dysprosium. So we had the opportunity also this afternoon to hear about extended Hilbert models, not the Buzz Hilbert, but extended Hilbert models. They are very nice. And in fact, this model, the advantage of this extended Gauss-Hilbert model is that in principle, it can be realized in the lab. Some groups realize it. Extended Gauss-Hilbert models in general in the lab, like groups like Francesca Fernando in Innsbruck, Chilman-Fao in Germany, Bing in China. So extended Gauss-Hilbert models are very physical in this context of dipolar atoms. So our model is a particular case of this model. So this is the connection between our Hamiltonian and the Hamiltonian of the extended three-side Gauss-Hilbert model by the special choice of the parameters. So this choice here and this choice here. So this is the relation between our parameter U and the parameter of this extended three-side Gauss-Hilbert model. And what about the feasibility of an experimental, possible experimental realization using dipolar BEC? Here I present a schematic representation of a possible trap geometry. So we have here three parallel laser beams here in blue, crossed by a transverse beam here in green, forming these cigar shapes in red, representing a deep dipolar BEC trapped in a triple well. And here, these transverse beams here perform the function of the external field controlling the device. Basically, when we slowly displace, make a slowly displace in the focus around this y-axis, this will produce this tilting in the wells 1, 3. So we can control the integrability breaking, this tilting by changing this focus of this green laser. We can make a lot of calculations, basically following the lines of this work of Chilman-Fao, and we can find some numerical values which are very, very reasonable. They are very realistic. For example, on these tables, we propose some realistic values for physical parameters for chromium, and here for dysprosium, which are dipolar models, dipolar atoms with large dipole momentum. For example, so values for the distance between the wells, possible values for the wavelengths, the weights of the lasers, for frequencies. So more details about this possible experimental realization or more details about this switching device can be found in our papers. Entangled states of dipolar bosons generated in a triple L potential in SciPoles. And in this paper, control of tunneling in an atomtronic switching device. And these results were also discussed in a Nature blog where for pedestrians, so how we cooked up an atomtronic switch. And they were also discussed, were also contributed to the International Women's Day, also in the Nature blogs. Okay, let me go now to the second application, is how to use the integrable 4 wells to generate NUM states. let me remind you what is even a Null state. Let me remind you that a Null state is a superposition of two different modes. For n particles, it has this form, n0 plus e to the 5 0n. This phase phi typically records informations in applications, so Null states can be applied in many areas, such as quantum metrology and sensing, quantum information, chemistry, biology, and much more. Curiosity Null states can also be found in arts, so in this work by Jonas Wood. What we want to do here, we want to show how to generate a Null state, and in addition, how to encode a phase into this Null state. Our approach is based on the formation of an Uber-Null state en route to a final Null state. And what is an Uber-Null state? To create an Uber-Null state, we consider this circuit of four wells, with a Fock input state, psi 0, MP00, M particles in site 1, here in cyan, P particles in well 2, here in blue, and empty sites 3 and 4. The first step in our protocols is to create this Uber-Null state. The Uber-Null state is defined here. We see in the first line what we have here, M particles in site 1, 0 particle in site 3, product, P particle in site 2, 0 particles in site 4, plus e to the 5, 0 particles in site 2, P particles in site 4. And in the second line, we have basically the same, but 0 particles in site 1 and M particles in site 3. So basically, this Uber-Null state can be viewed as an embedding of Null states within two-site subsystems. So now we want to describe two protocols to extract a Null state from an Uber-Null state. And for this, we'll consider a model of dipolar bosons confined to 4 wells, more specifically to a closed circuit of 4 sides. And the system has long-range interactions and can be described by the extended Bose-Hubbard model here. So extended Bose-Hubbard model are very physical. Here, U0 characterize the interaction between bosons in the same side. Uij are characterized dipole-dipole interactions of bosons at different sides, and the J's are the coupling for the tunneling. Our integrable model can be obtained for this model if these conditions are satisfied for the parameters. The integrable model has 4 modes, so we have 4 independent conserved quantities, the Hamiltonian, the total number of bosons, and discharge Q1 and Q2. From now on, we will only consider the integrable extended Bose-Hubbard model. To generate Null states, we consider the following, that the system is initially in this Fock state, as I said before, MP00, n equals to m plus p is odd. The system is in the so-called resonant tunneling regime, which is achieved for strong coupling. In this regime, it's very interesting because energy levels separate into bands, and an effective Hamiltonian, which dynamically equivalent to the integrable extended Bose-Hubbard model, can be obtained. It can be written in terms of discharge Q1 and Q2, enabling the derivation of physical expressions. And under this effective Hamiltonian, the time evolution of N1 plus N3 is constant, and the same for N2 plus N4. So basically, in this tunneling regime, M particles will oscillate between sites 1 and 3, and P particles can oscillate between sites 2 and 4. Now I want to describe 2 protocols for the generation of Null state. In protocol 1, the outcomes are probabilistic, while for protocol 2, they are deterministic. And both protocols consider the same initial state, MP00, and both protocols are built around the general time evolution operator here. H is the integrable extended Bose-Hubbard model. Mu and U are external potentials that make a tiltings in wells 2, 4, 1, 3, applied to a very, very short time. So these fields that break the integrability during a very short time. So this is the Null state generation scheme. In the first line, we have protocol 1. In the second line, protocol 2. Both protocols begins with the same initial state, MP00. In both protocols, we first generate an Uber-Null state here, which is a superposition of these 4 states. And in both protocols, in the end, we obtain Null state. In protocol 1, we can have one of these two null states, depending on what we measure in site 3. So this is probabilistics. And in protocol 2, we obtain this null state here. Here, the gradient colors are used to indicate that the state is entangled with the rest, and the rectangles represent external fields. So more details of protocol 1. Here are the steps that we implement to arrive at a null state at sites 2 and 4. First, we allow the system to have an integrable evolution during this time, apply an external field, and measure the number of atoms in well 3. So we initiate here with this side, allow an integrable evolution towards an uber-null state, apply a field, and then measure the number of sites of bosons at site 3. You can have either this or that. Depending on what you measure, we have another state. Analytical results can be obtained by employing the effective Hamiltonian. We find for the final state here, we have all states, but I'm presenting the last one. If we measure 0 particles in site 3, we have the first line. If we measure m particles in site 3, we have the second line. So these states can be recognized as a product of a null state for sites 2, 4, and the Fock states in sites 1 and 3. Very quickly, the steps that we implement to arrive to a null state for protocol 2. First, we allow an integrable evolution, apply an external field for a very short time, again integrable evolution, apply an external field to the other sides for a very short time. So these are the protocol: initial state, integrable evolution, apply a field for a very short time, integrable evolution, apply another field for a very short time, and arrive to a null state. Also here, we can get analytical results using the effective Hamiltonian. So we find this null state, this is a phase, and we have a product of a null state in sites 2, 4 with a deterministic state in sites 1, 3. We can compute the protocols. We can make simulations for realistic settings, and these fidelities are defined and computed using these formulas here. So phi denotes the analytical state obtained using the effective Hamiltonian, and phi denotes the numerically state obtained using the integrable extended Gauss-Hilbert time evolution. On this table, I present the fidelities for protocol 1, first column, protocol 2, second column, for 2 sets of parameters here, which are very realistic. In these tables, we can see that all the results have fidelities greater than 0.9, which is very good. These times TMU and TNU we choose, they are in principle very realistic. And this time for the integrable evolution, we obtain analytically. An advantage of these protocols is that the time evolution is independent of the total number of particles. In principle, we can do this in the lab. So here we discuss the experimental feasibility. This superlattice of a 4-site model can be achieved by a proper overlapping of different sets of counter-propagating laser beams with these vertical lines in orange to provide confinement. So more details about the experimental feasibility and more details of these protocols can be found in our papers, integrable atomic interferometry, and protocol designs for null states from last year. These results were announced in this Nature blog, and lunch will be served from me. Okay, now I'm going to some concluding remarks. So we have introduced a new family of integrable multi-well tunneling models, which may be formulated in different configurations and geometries. As the first applications, we show how to engineer a switching device by exploring the triple well. Then we also show how to generate a null state using the 4-well system. For future work, we can do a lot of things. We can, for example, do a more detailed analysis of the quantum dynamics using other initial states. We can also investigate the transport of atoms along the external sides of the open 4-well. This is a joint work with a student, Wallace. We can also compare and contrast the behaviors of open and closed systems. So what is the physical difference of these systems? We can also do many more things, develop other protocols to find other interesting physical states. We can also investigate the possibility of other physical applications, perhaps quantum motors, what happens when you break the integrability through periodic driving. So these results are parts of a project, Quantum Control Designed for Broken Integrability. The main goal is to open new avenues in the design and control of quantum devices using the notion of integrability and its breaking. So this is what we can offer in terms of integrability to find new devices which are now rising as a foundation for new quantum technologies. So I would like to thank my collaborators, John and Phil in Queensland, Ale and Leandro from Unipampa. This is a university in the countryside of Rio Grande do Sul. Karen, so this was part of her PhD, and Daniel, this was part of his master. He is now in the group of Francesca Ferlano in Innsbruck doing his PhD. And the students that are coming, and also Eric is a postdoc that moved now to Rio. So this is our team, the main contributors to this work. This is the Physics Institute in Porto Alegre. You are very welcome to visit us. So the collaborators, John, Leandro, Arley from Unipampa, Kari, and Daniel. So thank you very much for this invitation. Thank you very much for hearing. And once again, happy birthday, Chico. I hope that we meet in the future, that we will be able to meet again, perhaps in 5 years or perhaps in 10 years, celebrating again your birthday. So this photo is from 10 years ago. If you look Chico here, if you look him, at least I'm looking here in the screen, you see that he looks the same. Thank you very much.
Thank you, Angela. Questions? Well, maybe just being silly, but when I was a little kid in Physics 301, we saw this arrangement of resistors. That seems like your arrangement 2-2. And if you put something connecting site 1 to 3, it's called Wheatstone Bridge. So I was wondering if you consider, if you came to this idea and you could have the bosonic quantum Wheatstone Bridge. Yeah,
that's very interesting. I cannot see who is making the question, but I just saw now in the stacks of SBF in physics, there is a work of these bridges co-authored by Nikolai Zinner. Perhaps I'm not sure if you are one of the authors. So people are doing this. I have this paper. I really have it on my table, and I want to have a look. I think it was a PRX or a PRL, very recent, talking about this. I think there may be a bosonic analog of this type of work. I will look it as soon as I can. I don't know if you know this work of, I think, Zinner, and there is some Brazilian guy, first author. But this is very, very interesting. You see in the stacks SBF, they talk and they give us a short seminar about this. I don't know if you have seen. This is really interesting and really want to look this. I haven't done it, but this is quite interesting. Otherwise, it would not be a highlight. Yeah.
Okay, thank you very much. We have to move on, otherwise we come late. So let's thank Angela again. I hope to see you soon. Yeah. Also, Chico, your presence is here. I really wanted to come, so it was emergency. I hope you are well. And
okay,
so
Angela.
I'm so sorry. Yeah.
Now you have to come to São Carlos to bring this gift.
Yeah, I have to. My luggage was ready. Everything was ready. It was really very unfortunate.
You could send the gift, no problem.
Yeah. Yeah. So, congratulations. Nice to see you virtually.
Thank you, Angela.
All the best, really.
Okay. Next speaker is Shiran Shastri. Do we have Shiran there? Hi, Shiran.
Hi, Chico. Nice to see you.
Okay, can you
hear me?
Yes, clear and sound. Can you share your screen, please?
Yeah, okay. Right. Right. So,
Okay, yeah. Okay, Reentrant, all yours.
okay. Firstly, I'm delighted to be invited to this conference. I really wish I could have come to Brazil, but there are reasons, very good reasons why I could not come. And I sort of, I'm pleased that the organizers gave me the opportunity to present a Zoom talk. So really greetings to Shiko, whom I've known for several years through our common interest in certain journals. We were both on the editorial boards and came to know each other very well and had a lot of interactions, sharing impressions about science in the third world, which I originally come from, the first world, and things of this sort, and also integrability and problems of quantum integrability. So for this conference, I told the organizers, Jose in particular, that I really had a finished talk in my usual garden, which is many body physics, integrable systems, and stuff like that. And I also have a garden which is sort of being made, in somewhat statistical mechanical problems, in which I don't normally work. At least the current years, I haven't worked very much. But I was told that there is a school on statistical mechanics, and the audience may find the StatMech connected work to be of more interest. So which is why I kind of went in this direction of talking to you about the Lee-Yang zeros in some repulsive lattice gas models. I should also say that the origin of my interest in this problem really comes from my standard, bag of problems, which is many body physics, and rather interesting and surprising connections came to my mind, and I want to talk to you about that. So this work is going to be, it'll have the impression of being rather incomplete in the end, and that is correct. It actually, a lot of things are still being calculated even as I speak. So, but I'll give you an idea of why I think it is interesting, what some of the connections are, and what are the kinds of things we are thinking about. So I think in a conference of this sort, where we are sharing ideas, I think it's an advantage sometimes to talk about things which are currently being worked on and not quite complete. So I take your permission to talk about these things. Secondly, I'm actually very happy to have questions. Maybe in the middle also somebody can ask and moderators can raise a flag. Of course, at the end, I will have time for questions. So this is what I call as the ideas landscape. We have, okay, my arrow isn't working, so how do I? Maybe I just go back to this presentation. Is this good enough, you think, or should I go back to the full screen? Jose?
The way it is now, it's okay.
It's okay?
It's okay.
All right. I'll find this a little more advantageous. I can go back and forth easily. So I want to talk about some of the ideas which are behind this whole scheme. And in this scheme, these problems that we're working on, there's a bunch of people with me. Mohammed Sadek, who's a graduate student in Santa Cruz, Junaid Bhatt and Abhishek Dar, who are in Bangalore, Indian Institute of Science, now in ICTS, and me. So the starting point is actually surprisingly very far away from Lee-Yang theory. It's in Fermi liquid theory. So, Fermi liquids and some versions of Fermi liquids, maybe strongly correlated Fermi liquids, is an incredibly important subject with intellectual depth, of unsurpassed difficulty and rigor. And one of the cornerstones of this entire theory is the theorem of Luttinger and Ward. And many of you know that this theorem says that the volume of the Fermi surface of interacting fermions is an invariant. So when you turn on the interactions, the shape can distort, if you like, but the volume, and in 2 dimensions, just the area, remains unchanged. So this is something which I have been struggling with for many years, to see to what extent we can understand this better, what's behind this theorem, can we generalize this to other states of matter. So there is a paper which I wrote a couple of years ago, which is really the starting point of my entire interest in this thing. And I'll talk a little more about this paper in a few minutes. And this work led me to the problem of trying to understand the zeros of the grand partition function of interacting fermions, in this case, actually, many body fermions, and understanding how this lattice gas, quantum lattice gas, develops its partition function zeros, and how that sort of feeds into the Luttinger-Ward theorem. I say Luttinger-Ward because actually the most important paper here was not by Luttinger alone, but Luttinger and Ward. And this is the same Ward of the Ward identity. He's a major figure in field theory, who somehow our condensed matter people seem very eager to forget about. I mean, he's not referred to at all. Most people just call it the Luttinger theorem. It really is a Luttinger-Ward theorem, which gives the volume invariance of the volume. So in trying to understand these zeros of these partition functions, I ended up doing some finger exercises and talking to friends like Elliot Lieb. They said, look, there's no theorems available. You have to do some work yourself to find out what's going on. And I ended up working on small Hubbard clusters, painfully small, as you will see in a minute. But they give some information, and that information is very tantalizing but incomplete. So I felt really the need is to get into understand even classical lattice gases. And this brings us to the Ising model, of course. Ising model is nothing but the interacting lattice gas model. And here, as we all know, there are the ferromagnets and the antiferromagnets and the other randomly disordered, disordered Ising models and stuff like that. They're off somewhere here. But the basic classification is ferromagnets, which Li and Yang, were sort of one of the most important works in statistical mechanics, understanding how phase transitions happen. And these guys, they formulated the lattice gas analogy of the Ising model and gave us a deep understanding. And then they studied out of the blue the zeros of this partition function. And they showed this beautiful theorem that the zeros live on the unit circle for the classical Ising model. And then there was a lot of work in that area. In fact, this is an incredibly beautiful part of statistical mechanics, and it has like a finished look to it, thanks to the quantum generalizations due to Asano. Asano was really incredibly ingenious generalization of the Li-Yang theorem, and followed up by the heavyweight technicians, Ruel, Heilman, and Lieb, and so many others. Basically, we have now a complete picture of ferromagnetic Ising models and where the zeros live. As luck would have it, I'm not interested in the ferromagnets at all. I'm really interested in antiferromagnets. And this is an area where there is not much known. In fact, the zeros are not on any very simple curve. They're all over the complex plane, and they're very poorly understood. The early work on this from numerical work, really. Most of the work here, in fact, I would say essentially 100% of the work for the antiferromagnets is numerical and, severely limited by system sizes. So Suzuki, for example, was big enough, went to 6x6, 7x7 Ising models. C.K. Majumdar, who was my advisor way back in Tata Institute in the 70s, he went up a little bit more to 12x12 or something. And Kim basically did 15x15, 16x16 in some of the biggest numerical partition function calculations. And here, of course, the difficulty is that one has to compute the canonical ensemble partition function, not the grand canonical one. So one has to, I mean, in each number sector with number of downspins fixed, you need to compute the canonical partition functions exactly, and they become the coefficients of this grand canonical partition function. So you can't use things like Monte Carlo and so on. So there is no shortcut to understanding these things. You really have to enumerate the canonical ensemble partition function and assemble them into a polynomial, and then you study it by other techniques. And then this leads to other things, and even the numerics, we actually did some of the numerics. We were thinking we could beat Kim's results easily by maybe orders of magnitude with modern computation between the, let's say early 90s to 2020. Which means the graduate students thought that we could really do much more. We can do a little more, but frankly, not enough to celebrate. So we really stuck with the sizes of systems. So we did some numerics, and then we looked for analytical stuff, and then we have some results for the Bethe lattice where we can actually find the partition function and the zeros of the partition function of a Bethe lattice. But today I'm going to talk a little more about something even simpler in concept, but in practice is a remarkably non-trivial problem. So I'm going to talk about polynomials, which I can generate, which represent the mean field theory. So you might think of these as the partition functions of the infinite ranged models, if you wish. They're the same, really. So you can write down these polynomials and study their properties, their zeros, and see what the distribution of zeros is. And in particular, we want to know when the complex zeros begin to appear, and do they really mean anything physical? So let me begin with a few minutes about my paper here. So here, this is a paper which appeared already a few years ago, and I found really completely new proof of Luttinger's volume theorem, which also generalizes very interestingly to superconductors. In fact, in the superconducting phase, there is no Fermi surface, and yet there is a way of computing an effective Fermi surface from spectral functions, and the theorem here says that that's one of the best ways of discovering the Fermi surface of the non-superconducting parent system. So there is a lot of advantage gained by thinking about it this way. So I want to take a minute and tell you about what happened here, right? So we set up, starting with a partition function, where this little z is the fugacity, and this partition function is simply this thing, z to the m, and this is the canonical partition function. And we define sort of canonical chemical potentials as f of m plus 1 minus f of m, simply adding a particle, computing the canonical free energy. The difference is the canonical free energy. So we can rewrite this expression in terms of the canonical partition function, which can, replace the FMs. You can basically invert the problem and write the FM in terms of UMs. And it turns out that if we make an assumption of a positive definite canonical ensemble compressibility, namely, if mu of m increases with m. In other words, if I add an extra particle, the chemical potential can only increase. And you can relax this a little bit to greater than or equal to. But if you make this assumption, which seems a very reasonable thing for repulsive interaction, like in a Hubbard model, this is something close to compressibility, So you expect to have a positive and finite compressibility at even at low temperatures, including zero temperature. If I make this assumption, then we can show that the number of particles is basically in the zero temperature limit, like a step function. Every time mu crosses over one of these canonical chemical potentials, the number increases by 1. And just to complete the story, I would say that the basic result of this paper is that the number of particles can be expressed in 3 different formulae. One of them is this one I wrote down here. The other one is a theta function of the Green's function at zero frequency. So I think many of you might recognize the Luttinger theorem, Luttinger-Ward sum rule, as they call it, from this final form, that theta, that when the Green's function changes sign, the static Green's function changes sign, that counts a particle. So if I take a k-sum over the static Green's function, that gives me the volume in k-space of occupied particles, and that is invariant. So one really wants to show that this is exactly the same as the number of particles. And this is this formula here. And in between, there is the operational business end of the calculation is really in this gamma guy here. The gamma is a very interesting object. Take the log derivative, the time derivative, Matsubara time derivative, or the log of the Green's function in time space, and evaluate that at beta over 2, at exactly the half point in this imaginary time interval. So for some reason, this turns out to be a very special object. So this paper really shows that this guy is the same as this guy. And this guy is also the same as this guy. And therefore, this loop is closed and you have the Luttinger volume theorem, okay? So it's good news, and very happy, and you go home and write a paper. But the thing is, I haven't proved this. And I have really a glimmering that the grand partition function, or the grand partition function of the zero temperature limit might be something very, very simple, involving the chemical potentials. So that is what is interestingly provided by a paper which I ran into afterwards. So this condition is, as I said here, the chemical potential increasing is a condition for absence of phase separation, and in StatMech we teach this all the time. But it turns out that this condition was shown by Hardy, who turned it into a sufficient condition for a polynomial to be real-rooted. So, polynomials can be, in general, complexly rooted, and you can have roots which are negative, positive, all over the place. But if the coefficients are positive in the polynomial, then of course you can't have roots on the real positive axis. But of all the people, Newton was very interested in real-rooted polynomials in which all the coefficients are on the negative real axis. And electrical engineering control theory, that's another very important problem. People love these kinds of real-rooted polynomials. So Newton was happy enough with a necessary condition. If you take a polynomial to be real-rooted, then this condition follows as a necessary condition. But as a sufficiency condition, it's been very, very hard, and until I ran into this Hardy paper. It's a really beautiful work of early 20th century, I think it's 1904 paper. And to my amazement, I found that a lot of the things that he was doing are exactly paralleling the analysis that I had. So I kind of had a day to celebrate, that I was able to redo something which was done 100 years ago. And of course, normally you wouldn't celebrate that, but if that person happens to be G.H. Hardy, you kind of feel very happy about that. So Hardy basically considered polynomials, and in fact, even entire functions. This order of the polynomial goes to infinity, where these A's are the analogs of our canonical partition functions. And the inverse of A is written as a product of some B's, which he sort of came up with. And the B's are precisely these objects, these exponentials of the canonical chemical potentials. So Z, as I wrote in my paper a minute ago, is something like this. And Hardy basically had essentially the same formula, and he sort of, the tour de force, absolutely beautiful theorem. He shows that if the B's exceed, the B's increase, and if the ratio of the B's is some number, and his best estimate was 3, then all the roots of F are real. And if I translate this into the Fermi gas, what this requires is that the canonical chemical potential difference must be greater than kT times a number which is related to this bound, log 3. And actually, I worked pretty hard on trying to improve this bound, and it didn't change things very much. I could improve it a little bit to something like 4, but that doesn't really matter. It doesn't really matter. What this tells me is that if I recognize the difference of the chemical potentials as the inverse compressibility, then this is simply telling me that when temperature is low enough compared to some finite number, I get a real rooted polynomial. And what that means is that, okay, what's the physical implication of Hardy's result? It says that t equal to 0, a Fermi system satisfying this with a strict inequality. And there's actually even a bound there, a number of order b, which I'm going to ignore that for a minute. This means that the partition function is in fact just like a free Fermi partition function, exactly like a free Fermi partition function. And these energies, epsilon j's, are real numbers, and they are actually the canonical chemical potentials. So that's really absolutely lovely result. I really was not prepared to believe something so simple can be shown. So I found it quite interesting, and I chased this up a little bit and basically tried to see what the implications of this are. So this is something not yet published. I'm going to go. So I basically want to talk about. So this set me off trying to figure out what the roots are like in the standard models that we deal with in many body physics, the Hubbard model, for example. So I took the Hubbard model, and indeed, there is a little opportunity for me to proselytize. We've created a Mathematica package called Dirac Q, which is available on my website or on GitHub. And what this does is basically teaches Mathematica all the commutation and anti-commutation results of fermions and bosons, and what have you. Basically, if you have some weird statistics, there's a very simple way of programming that statistics into Mathematica. So then you can write down the Hamiltonian symbolically, and it creates a matrix for you, So it makes life easy for people, some theorists like me who are better at symbolic work than actual numerical work. So I did this and studied, a few clusters, and I want to show you some of the results. So indeed, for positive U, one finds that all the roots are on the real axis, negative real axis, and they evolve with, you can study the T prime dependence, U dependence, etc. But at least for the systems that I could study for a cluster of 4 sites, which is a terribly small system, all the roots are negative and real. But the one thing which is interesting is that if I turn the sign of U, make the Hubbard model attractive, even on the small system, all the roots immediately go complex. So roots going complex happens due to the sign of U in these problems. And clearly there is no phase transition, these are finite systems. So they're not really connected to, any thermodynamic transitions. But the interesting thing is that the Li-Yang zeros know about the signs of the interaction. And this is interesting because, even today you'll find many people arguing back and forth about, is the Hubbard model with positive U a truly repulsive model? Is there some sense in which it can become attractive? So the attractive versus repulsive is a, topic that we can talk about and talk a long time about, especially if you have a glass of beer. But the Li-Yang zeros give you like a precise result to that. Okay, so the questions which arise is, what about general lattice gases, repulsive lattice gases for large systems? Are the roots complex? in general at any t, or do they become automatically real? What fraction of roots are complex? And do complex roots necessarily imply a change of phase in the Ising model? So these are questions you can ask, and they're relevant to understanding more deeply the Luttinger-Ward theorem. Luttinger-Ward roots look real up to some system size, but obviously there's no guarantee that they won't go complex. So when they do go complex, what is the meaning of those complex roots? So those are the questions I'm ultimately interested in, and I'm looking for some answers in these somewhat simpler classical models. So we looked at classical models. The 2D Ising antiferromagnet, which Kim did, and our group has done a little better. I'll show you a few results from that. And then we actually found much more sort of satisfaction in looking at infinite dimensional models in which it's very interesting to write down polynomials, which become the mean field theory for large polynomials. Okay, in other words, the mean field theory is often understood as a saddle point of some theory or the other. So you can write down actually simple enough polynomials which can be written down for finite systems with no phase transitions, but they know about the incipient phase transitions. They have all kinds of rich behavior, and the Bethe lattice is another system which we have worked on, and I'm not going to talk to you about that today. So here is the result from the actual 2D Ising model in the biggest system size which is available. So here is above TC. So the 0 is out here. Okay, so all this is negative real axis. So this at TC, you still see nothing much happening here. And in fact, you don't see any roots leaking over to the right. And even below TC, at half of TC, all the roots are to the negative real side, and they don't come down, although we know from the phase diagram of the 2D Ising model that for a finite magnetic field, there is a phase transition. In the HT plane, there is a curve on which there is a phase transition, and the zeros really should come down, but they don't in this somewhat constrained system, too small to show that kind of behavior. So what are these mean field models? So a minute about the ferromagnet. It's actually a very simple thing, but essentially start with Ising, cumulant theorem, and take these cumulants in the unperturbed, basically pure, fugacity terms, and then throw away the second cumulants. And this becomes now the square of the average of sigma. It just counts the number of particles which are present on the lattice. And so we think of upspin as a particle and downspin as a hole. So ultimately, this is pretty straightforward. You get the partition function, combinatorial factor, just the entropy factor, and the energy is basically a Gaussian. And this kappa is something like inverse temperature. So talking a little bit about early work, I mean, Suzuki, way back in the early 70s, wrote a good paper on the mean field theory and the Li-Yang zeros for the ferromagnet within mean field theory. He was using basically analytic continuation or the mean field equation of state to guess where the zeros in the complex magnetic field would be. And there are some beautiful papers by Kortman and Bob Griffiths, which continue with that direction. So what we can do actually is not worry about any analytic continuation. We really have a polynomial. We can study that. And we can study this polynomial in one of two ways. We can find the roots using a root finder. Or we can use some analytical techniques like saddle point methods, which actually work very well for the ferromagnet. So numerically, we can find roots for any up to 100 or even 300 with just Mathematica. And I want to show you the numerical roots compared with some of the saddle point exact solutions. So here is the numerical root finder for a polynomial of order 100. And K here is 0.8, which is slightly above TC. And this one here is K of 1, which is exactly TC. So you see the roots are, beautifully on the unit circle. And as you go to TC, the roots come closer and closer to the real axis. And that dependence is very well described by the standard critical exponent 1/2. And here, these circles is what happens with the saddle point technique. Saddle point technique, you can find the roots for n big enough. And in practice, it looks like n bigger than 10 already gets you all the roots to third decimal place accuracy. And when you overlay these two guys, you see that you can hardly distinguish between the saddle points and the actual root finders, okay? Now, what about the antiferromagnet? So for the antiferromagnet, you can do something similar with the flipped sign of J, and you can do a little analysis and show that this is also a Gaussian of some sort, where you have the number of particles in the A sublattice and the B sublattice and their product. Basically, they define these local magnetizations, the two sublattices. And when you do that, you find basically the antiferromagnetic mean field model, roots. So this is for about 256 sites, about the same size as Kim's biggest and our biggest systems. So at above TC, the roots are all over the place. In fact, we have some exact proof that these roots are the roots of the Hermite polynomials. So that's an interesting analytical result, which I'm not going to have time to discuss with you, but close to zero on the negative real axis, their density and even the location is given by the Hermite polynomials. And there's a nice theory behind that. But for you, I mean, I would say at TC, you see it begins to curve over and you have something which is creeping into the real positive real axis. So these guys are expected to come down. And in fact, at 0.5 TC, they do come down. And, this coming down in the roots approaching the real axis is simply easy to understand. In the HT plane, you're basically trying to approach the TC at finite uniform magnetic field. At uniform magnetic field below the HC value, you do have magnetic order, and that phase transition, is also continuous phase transition. So you do expect these roots to come here. So we can show that within this, within these guys. The only limitation that we have with this technique is the root finders. Basically, the polynomials are trivial to generate. So can you find better root finders than Mathematica? That's the chance of doing that. And really, our money is on the saddle point method. So we've tried several things, and this is work in progress, and I hope we'll see some end to this. But I must say that the saddle point technique is pretty hard for these types of polynomials for reasons which I'm afraid I don't have time to talk to you about. But that's where we are putting our effort on. And finally, quantum computers have recently been applied to find Lie-Yang zeros, but the sizes are even much smaller than the ones we have. So here again, the hype seems to be much greater than the on-ground reality. So I would say that we are still on a trip, which we haven't concluded totally, but the journey has been very, very interesting. And I would say that it's been surprisingly challenging. When I started out saying I'm going to study something which is related to mean field theory, the hope was, this is a weekend problem, finished in a weekend. But no, it's much harder because finite systems, trying to understand the mean field theory for finite systems is an incredibly hard problem. I should just say that those of you who are in the audience who know about integrable systems, of course, know this. I mean, Michel Godin had this incredibly beautiful paper trying to understand the BCS mean field theory of attractive fermions. So, I mean, if you talk to any graduate student, he would say, yeah, I mean, we can solve it. We can solve the BCS problem trivially. It's exactly, and the BCS is the resulting solution. But Michel Godin pushed further, and he asked the kinds of questions that we sort of getting into here, namely for large but finite systems, how exactly is the order reached, and other stuff, So, so connections are interesting to other problems like Luttinger-Moore theorem. So I would say I'm having a lot of fun, and I thought I would share some of this with you guys. Thank you very much.
Thanks a lot, Shiran. Questions? Comments?
Hi, Shiran.
Yes.
Yeah, it's Chico.
Oh, yeah. Chico, yeah, hi, Chico. Can you see me?
Yes, yes, of course.
Yeah.
You are seeing me?
Yeah.
No, probably not. No.
Yeah, I see you. I see you,
Okay,
Chico.
okay.
Yes, I see you.
Right.
Right.
Yeah. Tell me something.
Good to see you.
This beauty of the zeros showing you how to go to the non-analytical behavior, but do you think that there is a possibility or somehow, like you have, for example, models that has conforming variance, okay, so when you go in the continual limit, you have all these structures of the, the levels, whatever. If this type of thing could give some relationship with the zero so that we can detect something like that?
That's a really good question. And I would say there's a, like Suzuki did, for example, we know the equation of state for the mean field model, and we have some understanding of the critical behavior. So we could start from there and then do analytic continuation and try to understand better some of the exponents, which are, and the connection between exponents. So this is a game which has been, played very well, very effectively. Like Tarde, for example, has beautiful papers on understanding the random freelizing model, the Lee-Yang zeros, and by studying exponents and so on. Indeed, conformal theory is a more refined version of that sort of an approach. But here, the kind of questions that I am interested in are much more like when is the onset of complex roots? What is the signal for us? Maybe the answer is not much, but then even that would be clear if I can compute the density of those complex zeros. So I should be able to do something with the complex zeros and get a feel for it. Now the trouble here is, mathematical physicists have beautiful and perfect answers for some of these things. Like the paper of Heilman, which says that Heilman and Lee, which says that in certain models, all the zeros are on the negative real axis. But then you have no intuition as to how that happened. What happens if I tweak the model a little bit? What happens if I, it's a little bit like how to make a joke, how do the plebeians understand the market as opposed to the aristocrats, So I'm actually very much in the position of a plebeian. I really don't understand what's the origin of these complex roots. And, can I see the thing cooking? What exactly is happening? So for me, I think conformal theory is a tool of the aristocrats, at least currently. Maybe I will be an aristocrat tomorrow, but today I want to be a farmer,
Okay, thank you.
Sorry.
More questions?
In your clusters, using mathematics in the beginning of your talks, how many particles n can you compute the roots for the Hubbard model? For the, I think you said 16, yeah?
Yes. So I actually stopped very rapidly with 4 because I knew that I cannot really go beyond 8 or something. For the Hubbard model, if you look at the exact diagonalization problems, people have done up to, I don't know the record, but I think it's about 18 or 20 or something like that. For the Heisenberg model, people have gone up to 30s and 32 and 34 sites, 36 sites even. Hubbard, bigger Hilbert space, so smaller NS. So I think 8 up to 12, 14, 16 is possible. Yeah, but I was actually making a pitch for, pardon me?
You could improve it until 12, you think, yeah? 16 maximum.
I don't. 16 sites may be possible for the Hubbard model, but not with the Mathematica package that I have. Mine is a little package which runs on laptops and it works for, but yes, I mean, there are heavy duty computational experts who do Hubbard model for a living, and they can actually make much bigger systems. But can they compute the entire spectrum? And can they compute the entire grand partition function, which is a much more demanding question than what many of the high-powered numerical people do. I mean, people can do for the ground state much bigger systems, But what we want here for the Liang problem, we want the entire spectrum, and that's a considerably harder problem. So I wouldn't be surprised if the limit is closer to 10 actually for this kind of a question.
Okay.
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 I don't see any further questions. Let's thank Sharon again.
Okay. Thanks.
And the last speaker of the session, Silvio Damen from Rio Grande do Sul.
Alô? Alô? Okay. So since I have a few minutes, I'll start by thanking the organizer for the opportunity of being here. 10 years ago, I couldn't, so this is a great chance to meet Chico again and say thanks to him and happy birthday personally. But okay, so thank you. This has nothing to do with the things we've been hearing until this point today, but I will show it actually has a lot to do with all of us, right? I'm going to show you how to use physics to understand history. But back in 1985, as I came to São Carlos as an undergraduate student, we had our first physics lecture. And well, we went half an hour before the lecture started, first lecture. We were all waiting. And then came through the door Chico Alcaraz. He was my first teacher in São Carlos. And you've seen this morning a picture of him that Fabian Esler showed. So imagine that guy, but with a beard. But not a simple one, a lumberjack kind of beard, Barbara Raiz, really, really. And it was really intimidating. And from intimidating, it went to scary because he looked at us and he said, well, I'm here to separate the wheat from the chaff. Eu estou aqui para separar o joio do trigo. He said that in a different way, but that's what he said. So, we're going to get killed by this guy. But as time went on, it went from scary to fascinating because Chico was a great teacher. He was really, the way he solved problems was completely different from what we had in the books. And from that moment on, we were really, we became Chicolinos, followers of Chico. And I'm going to tell you a little bit of this story today. So I'm going to talk a little bit about networks and show what it has to do with all of us. But, networks are graphs. So there's a lot of beautiful mathematics behind it. And they're extremely abstract because they can represent anything. You have nodes interacting with each other through what we call links. So they can be used for, whatever you want. But especially in history, when you have some historical events that takes hundreds of years and thousands of people involved, they become very complex. And historians have no way of dealing with so much information. They need some tools to look at these networks and understand what's going on. Now I'll show you a historical network, which I'm always amazed because when I show people this network, people look at it, they don't realize what this is. Yeah, I mean, it's a place, right? And it's Europe, but what does it actually represent? Those are actually the most important Roman roads and seaways during the Roman Empire, right? So it's a very beautiful image, I think, of all the roads connecting the major Roman cities. And, but you can extract information out of it. You can, for instance, use this image to calculate a lot of quantities like closeness, betweenness, and things that people use when they're using networks. I'm sorry.
The colors.
Oh, the colors. I'm sorry. I couldn't hear you. I'm hearing impaired, so I have my they don't just for because you're pretty. Okay, here they mean something. They mean how closeness is a measure, right? The redder they are here in this to the left side means the more important the centers are. But that is just for visual reasons. They have no meanings, the colors actually. So, but you can actually study this and do things. So, what happened was that we have to be careful because when you're talking about history, right? Humanities, it's a really complex subject because history, when you say, okay, let's talk about Second World War, let's talk about Napoleon, we are always reading and understanding history the way it is told us by someone. So this is something that historians tell us. This is very important to make this difference. The facts were there, but someone told them, and when someone tells something, he probably has a bias. So it's very complicated to do physics or use network theory because humanities, that's the city where the idea of graphs showed up, which was Königsberg. It was a city which had a very important problem, the seven bridges problem of Königsberg. And Euler solved this problem and created graph theory. But while historians look at that and see that beautiful image, with all the intricacies, we physicists, we say, no, that's just what's on the right-hand side of the picture. We reduce those things to a series of dots and links, and with that, we may lose a lot of information. So the use of networks in history, it's a little bit problematic, but we should try anyway to do something. So we had this problem, which was some historians asked for help to develop some tools which would help them understand a little bit better how networks could be applied to history from it's a bird's eye perspective. You're seeing things from a very distance, from very far away, without worrying too much about the details. So see if it's possible to use these tools, apply these tools, see if these tools are good, test them, and if you can test them, see if you learn something new, which they did not know before. So then came Chico's rule number 1, which I learned when I was a student. He said, if you want to do something, Silvio, look for the best. Right? Look around you. See who is here. So I had people here today. So this is something I learned from Chico. So I said, okay, if you want to do something, if you want to learn something, just look for the best. And I was lucky to have some collaborators. I'm unimportant there. Don't worry about me up there. Right? I'm here. But these guys here, they are really good in network theory. This is a computer science. It's really, really good too. And these historians, they specialize in Roman history, and they are the most important living historians in this field today. So we got together, and I was lucky because actually this guy I had worked with, he's the brother of this girl here, who's a great historian. So we had this natural connection, started discussing, and they came with a problem which was, look, when you look at they study Roman history, right? And when you study history, women are usually not really described. They're usually described as what they call peace weavers, right? What was that? Well, you had a kingdom was fighting another kingdom, and so when they wanted the truce, what they would do, they would marry the daughter of a king into the family of another king, and end the war. So that's how women were depicted. But is it true? Is it always the role they had? Weren't they more active in society and things like that? So they were motivated by this idea because they were reading some work where women were depicted as being very important, but they wanted us to help them show if these women in this story were really, really important. So can we use networks to do that? And they came with this book, right? I'm sure most of you probably haven't ever heard about it, but if you want to know anything about the history of Great Britain between the invasion of Julius Caesar until a little bit before the Vikings invasion, that's the only source that you have on Anglo-Saxon history, right? But what's more interesting is the guy who wrote this book, because if you remember your Latin, the book starts with that phrase which I've written down there, which is exactly ipsis litteris what Pliny the Elder wrote in his Encyclopedia of Geography. So the guy who wrote this, he was studying, you know, the old Roman scientists, so to say, they were Roman. And his name was actually Bede. So we don't know Bede, but actually Bede should be known to us because most of what survived of mathematics, which came from late Roman Empire into our days, we actually owed this guy because he was a scholar, and he was a monk, of course, but he was a scholar, and he had a beautiful library, the best library north of the Alps in Europe. And he took all this work, he started writing mathematics manuals, you know, books to teach other monks to, you know, do mathematics, because he was actually interested in calculating calendars, what's called time reckoning or computus, it's a technical term for that. So he was a very important polymath scientist of his time, but he became famous because of the book he wrote about the history of England, which I told you is the only source of information we have. So, so we took this, we didn't take this book. This historians I work with, they took this book and they started building the network of interactions in this book. And this network has 473 people, of which 62 were women. There are basically 2,300 connections. And the categories, the edges which connect people, they have different qualities, so to say. That's called the multiplex network. And the kinds of relations that you read there, it's not really important, but basically that's the kind of relations that existed between people at that time. So people were related by blood or, you know, what's called kinship, but they were also related by something interesting. It's called monastic family. Most of these monks, they were given to monasteries when they were really, really young. So the family would give a boy or a girl to a monastery, and they would be raised in this monastery. So the monks and the nuns became their fathers and mothers. So they considered this a family. It's called monastic family. So we tried to analyze this network to see the role that women played, and doing some calculations and running some programs. And we used something which is called supernatural. It's very interesting because Eduardo, when you think about history, these guys lived in a monastery. So for them, the world was, everything that happened because God wanted that way. So for them, angels intervened in daily matters. So angels could kill you if you were not good enough. They could, you know, do whatever. So supernatural means there is an angel which interceded and did something. And they really believe that happened. I mean, there's a case of an angel who killed someone. Of course, he was killed by someone else, but they believed it was an angel, right? And we use this, quantity which is called communicability, which is some kind of betweenness. It's mathematically well defined. And I'll just show you very quickly the equation. You have what's called the adjacency matrix, where each element of this matrix to the power k means the number of walks between nodes. And we define communicability as the resolvent, as an expansion of powers of this matrix. And there's a lot of beautiful mathematical structure behind this thing, but I'll just skip it and go straight to the result. So when we ran these things, when we used our algorithms, we had this communicability. It's normalized. We found out there were 4 women which appeared to have a very high degree of connection. But the problem was these 3 of them were wives or daughters of kings. So you say, well, it's natural that she was well connected because she was connected to someone who was very important. So you see their names there in this kind of, I don't know what color that is, but let's say rose, right? So I said, well, how do we know if they were really important? So what we did was we ran the same thing, but we did the following thing. We just calculated that thing, and then we extracted one, for instance, Unfled was the daughter of a king. So we said, let's take this king from the network and see how her values change. And you see that by taking some of the most important people, which were kings or some very important archbishops, you see that their values fluctuate a lot. For this Unfled, she really changes the value of her betweenness or communicability depending on if there are some very important people connected to her or not. But this one lady here, and this one actually, they were basically constant. Their values were not affected by changing the structure of the network. So we thought, okay, this means something. It means that I'm plotting this communicability, which is a kind of a measure. So if you take some important men away, they just, they fluctuate. But in this case, it's not fluctuating. So, and you know what's very fascinating about this? I have names there, but we work with numbers. They gave us a list. We transformed these names, like Hild or Etheldreda, which is the modern English Audrey. And we transformed it, and we used numbers, and then we plotted, labels, 1, 2, 5, whatever. And then we gave them this, and they read it, said, okay, but this is this person. And they knew that, for instance, this woman should be, they expected her to be very important, and to be important on her own. So what's fascinating from my point of view is that you just have a network, a mathematical model of something that happened in history, and somehow you can see things that the importance or unimportance of someone from operating on matrices. And we then ran, just taking away all men which were not connected to any women. And we actually calculated this thing again. We ran the programs again, and we saw that this nun, she was an abbess. She was really, really important. And the results confirmed what historians had already suspected a long time ago. But just to show what a network looks like, this, basically the network that's represented in in those graphs that I showed you, where the size of each of the spheres or circles means how important these people were, right? Then we come to some results which mean basically, okay, this Bede was an exception at that time because he described in his work women, and he gave them really power in the sense that he really represented them as they were. Some of them were powerful, let's say, in a sense, because not because they were related to powerful men, but just on their own. And you can use networks to understand some historical things, but you have to be really careful because the interpretation, working with historians is very, very complicated. Because if I drop a book and say, why did the book fall? Right? I ask you. He'll say, well, come on, it's gravity. If you ask a historian to drop a book, say, why did the book fall? They'll answer you with another question. Well, did you ask the book why it fell? Or it's really difficult to get a straight answer from them because everything is really kind of, it's a matter of opinion. So we go to Chico's rule number 2. We use Chico's rule number 1 to understand why I work with historians and the best ones I could find. So the other thing I learned with Chico is you have to know to whom you should take your hat off, right? So I said, okay, let's try to see. Chico was my advisor in iniciação científica, then mestrado, then I started PhD with him, then I went to Germany with him, with Vladimir, and stayed in Germany and finished with Vladimir Rittenberg. So I did a network of the collaborators of Vladimir Rittenberg. If you ever worked with Vladimir Rittenberg, you were here, right? Chico is this guy here of FCA, okay? But Germán is here. Everyone who's ever worked with Vladimir is here. So, but this is just the collaborators of Vladimir Rittenberg. So I said, okay, let's see how many students he formed, how many people worked with him. And then I have a network. It's very hard to see because it's a huge network. So here is Vladimir Rittenberg's network. This is Vladimir, right? Chico is this little dot here, okay? And these are all PhD students of Vladimir who actually are still in universities working. And you see something interesting here. This guy is Hans-Peter Niels. He was the first PhD student of Vladimir, and he actually went into string theory. So he created a network of his own. You see that all other students of Vladimir, which are basically doing statistical mechanics, they are somehow all in the same this giant network, while this network here doesn't have much to do with this one. So you can look at in a different way by blowing up and just showing the PhD students of Vladimir, right? These are the people who, he had a lot more PhD students, but the ones who are still working in the universities are depicted here. So, and the collaborators also, with its respective collaborators. So I said, well, I'll do the same with Chico, right? Because Chico is just a small, unimportant dot in this network. So let's see Chico in his full regalia. And this is Chico's network, okay? I got this from Lattice, okay? I didn't go to the Web of Science because it's a lot of work, but if you ever worked with Chico, right, you are here. Now, the large one, the big names, right, written, these are his students, people who studied under him, right? Like Malvesi, myself, during my master's, and Xavier, Zé Cândido, everybody's here, right? And some people, Juliano is here because he was a student of Marcio. Well, I didn't, actually, you can see this evolve with time, but I didn't have time to do this because it's a lot of work, you have to do it by time, but you can see it really growing, it's really fascinating. You see how one person is able to create, many different clusters, and these clusters propagate. So this shows Chico's, in a way, influence. There are some characteristics, I won't go into the details, but there are some differences between his network and Vladimir's network, because there's a difference in the way professors advise in Germany and in Brazil. There's a different way of doing things, right? Usually in Germany you have very few professors with lots of postdocs, assistants, and a lot of students, and he puts his students to work with themselves. So you see, when you look at Vladimir's, for instance, you see a lot of more crossing, because he would put all students together in one room and would have you work together. So I worked a lot with my colleagues there, and you see a lot of links going back and forth, which is not something good or bad, it's just the way things work. here. So that's why in Brazil you have more, Chico has André interacted with some of us, interacted with other people, but it's mostly you have this separate, because being an advisor here is much more a one-to-one relationship. And then this is Chico's network. We can look at it later with detail. I can send you this, this image because your name, most of you here, your names are there, okay? And then I came to Chico's rule number 3. I think this is the rule one of the rules that I think is the most important. I once asked Chico, why do we do what we do? He said, Silvio, it's not about the science, it's about the people you form, the people you train, right? So this is something learned from Chico, right? So what Chico told me is, first, look for the best, recognize the values of, when say take your hat off, recognize the values of other people, and look after people. You are dealing with people, they are not machines. So if you ask me, what is Chico to me? For me, I'm serious, Chico is the epitome of kindness. I've met many people in this field, but Chico is one of the kindest guys I've ever met. If you ever had a chance of working or have contact with Chico, you know what I'm saying is true. Now, Viola Davis, which is a famous American actress, she was given a commencement at Barnard College at Columbia 3 years ago. And when Chico said, look after people, or, of course, Viola Davis' English is better than Chico's, so she put it in a nice way, which I call now Chico and Viola's golden rule, which is you can either leave something for people or you can leave something in people. And there's a big difference. And I think that Chico, he not only left things for people, but he certainly left a lot of things in people. And that's what I value the most. I'll finish with a story that I have. When I was in high school, we had to study this poet. His name is Robert Frost. He's one of my favorite poets. And he has a beautiful poem called The Road Not Taken. It's beautiful. I know it by heart, but I won't tell you the whole poem. But the last stanza says, I shall be telling you this. Somewhere, ages and ages hence, 2 roads diverged in a wood, and I took the one less traveled by, and that made all the difference. Chico showed me the road which was less traveled by, and that has made all the difference in my career. So for that, I thank you, Chico, and happy birthday. Thank you.
Thank you.
Very interesting talk. And I'd like to ask if you're willing to answer this. Of course, you can just say you don't have any answers at the moment. But what other hypotheses in history do you think could be tested with this approach?
I have the, there is this thing in history called historicism, or also called great man theory, which says basically the following. History is defined by very few people, great men, great women, which change the course of history. And historicism is something a little bit deeper, which means there are rules. So history repeats itself. Now, there are different kinds of historicism there's spiritual historicism, which, okay, there's some power behind everything telling where things are going. There's economics historicism, and there is also natural historicism. There are rules in nature which basically, make things be the way they are. So I think the idea, which I didn't discuss here, but which was behind what I learned from the historians, is this idea of great man's history, which goes back to Thomas Carlyle, the 1800s, which says, I mean, it's very appealing. So, okay, Napoleon decided things, you know, George Washington did a lot of things, and, you know, whatever, you know, pick all these famous people, Queen Victoria, I don't know. But now historians are starting to look that history is not, these people were, of course, important, but there were all the agents, all the different actors which actually played a role. And I think that's where this thing can happen, because it can show that there's a lot of influent people, a lot of people who were, these networks are very important, but were not given the credit they deserved. So I think this is a hypothesis that can be tested. That's actually my personal point of view. Okay.
Here.
Yes.
First of all, I thank you for a beautiful talk. I enjoy a lot. And I have to say, the subject you choose to apply mathematics is very fluid, I would say.
Yes.
Now, is a comment. Years ago, I wrote a book on Divina Commedia, Dante, which is one of the, I mean, greatest book ever. And I
La
tried...
Selva Oscura.
Sorry?
La Selva Oscura.
And I would like to force how much mathematics allow me to understand the greatness of this. So I start doing what probably is called a computational linguistic. So I start, for instance, counting occurrence of word. You would expect for a book like Divina Commedia, the most one will be God or love. Not at all. The most one is eyes.
Eyes.
So the guy was much more interested you are looking at someone.
Oh.
Then I make statistics. So the next one is word. Then earth. God is just fifth. God just fifth.
Oh.
Then you can understand the entropy of the book. Namely, each book is made by word which means something and word which connect things.
Yeah.
Like hand, that, this is you need to use. Now, I compare this with other books. So Divina Commedia played really well. The best one is Leopardi. I'm just reading what I had. The second best is Kafka. So Kafka is the most, is the book that conveys more information with the number of words. Then there is Pirandello. Then, okay, Divina Commedia, then Marco Polo, Il Milione.
Il Milione.
I mean, I'm using this book, this old book because the language itself was rudimental.
Yeah.
So you can understand something there. And Bibbia played pretty bad. In terms of entropy, it's very entropic. So a lot of words which means nothing, essentially. So what I want to say is fascinating indeed what you are doing. And when you try to apply mathematics outside the usual realm, always discover something incredibly, juicy.
I know it's late, people are tired. Just a small comment. There's a lot of people from, because, to get these networks, you have to read the book. It takes a lot of work. So what people are trying to develop is automated reading. You go there and you try, and then they start to study, these connections, how many words, if they make sense. And so there's a lot of research, especially in natural language recognition, and you say something to Google, it translates to you. So it's a kind of, it's really fluid. It's really hard to you can take it the way you want, in a sense. Yeah.
But I appreciate
thank
a
you
lot.
for the.
Thank you.
More questions, comments? Well, if not, we are done for today. Let's thank Silvio again, all the speakers of the session. A couple of announcements. Remember, if you are interested in going to the dinner tomorrow night, please send me a message so we can do the reservations. And we resume tomorrow at 9. Have a good night to all.